Part 1. Chicxulub Impact. 66 million years ago, a cosmic messenger the size of a small mountain hurtled toward Earth, its fate sealed in the shallow tropical seas off what is now Mexico's Yucatan Peninsula. The asteroid's violent collision carved out a crater over 150 kilometers wide and unleashed energy equivalent to 10 billion atomic bombs. In the instant of impact, an incandescent fireball vaporized rock and water alike, launching a towering plume of superheated debris tens of kilometers into the sky. This primal explosion marked the beginning of a global cataclysm that would reshape climates, oceans, and the very course of life on the planet. Within moments, tsunami waves hundreds of meters high radiated outward, obliterating coastal ecosystems from the Gulf of Mexico to the far reaches of the Caribbean. The force of water crashing onto continents scoured river valleys and washed inland forests into oblivion, leaving behind chaotic sediment deposits that today reveal the violent choreography of the impact. Fish and marine reptiles were swept into shallow lagoons, their carcasses buried in layers that bear silent witness to the suddenness of the event. Inland, the roar of collapsing shorelines merged with the thunder of falling ejecta, drowning out every other sound on a planet in its final hours of the Mesozoic. As molten rock and vaporized material rained back onto Earth, the sky became a furnace. Glowing spherules of impact glass streaked through the atmosphere, igniting wildfires across continents. Paleobotanical evidence shows an abrupt burst of charred wood and charcoal in the boundary layer, indicating entire woodlands burned within days. The global surge of smoke and soot ascended into the stratosphere, forming an impenetrable veil that blocked sunlight for years. Under the ashen sky, temperatures plummeted, plants perished without photosynthesis, and the food chains that had persisted for millions of years collapsed in rapid succession. Beneath the smothering dust, massive releases of sulfur dioxide from vaporized carbonate and sulfate rocks formed reflective aerosols. These particles further darkened the skies, reflecting solar radiation and plunging surface temperatures by more than 10 degrees Celsius. Paleoclimatic models describe an impact winter of prolonged darkness, where freezing nights alternated with feeble cold days. In the ocean, phytoplankton, the architects of the marine food web, suffered mass die-offs as light penetration dwindled. The resulting marine famine rippled upward through fish, marine reptiles and seabirds, mirroring the terrestrial starvation gripping herbivorous dinosaurs. In the months that followed, oxygen-rich air and lingering heat from re-entering ejecta created brutal thermal spikes by day and sub-freezing chills by night. This double-edged thermal shock stressed organisms already reeling from darkness. Tropical regions saw daytime ground temperatures soar above boiling, while polar zones experienced sudden freezes. Such extremes would have overwhelmed physiological tolerances, fracturing ecosystems in ways that no single stressor could achieve alone. When the aerosols finally settled, Earth emerged into a new kind of furnace. Carbon dioxide from wildfires and vaporized sediments had accumulated, trapping heat in a runaway greenhouse effect. Temperatures surged above pre-impact levels, causing acid rain as sulfuric compounds dissolved into precipitation. Rivers and lakes turned acidic, stressing freshwater communities. The climate roller coaster, darkness to cold to scorching heat, subjected survivors to relentless stress, while soils leached nutrients and entire ecosystems sought fragile equilibria in the wake of planetary upheaval. Remarkably, not all life perished. Small mammals, omnivorous birds, crocodilians, turtles, and amphibians found refuge in burrows, dense forests, or aquatic havens. Their ability to consume varied diets from carrion to seeds and detritus allowed them to weather the collapse of primary production. Amphibians, with their aquatic larvae, bypassed the need for plant food altogether. These survivors formed the foundation of a new ecological order in the Paleogene, radiating into forms that would come to dominate land and air. The Chicxulub event left an indelible mark on Earth's crust. A global layer of iridium-rich clay, an element rare on Earth but abundant in asteroids, sits precisely at the Cretaceous, Paleogene boundary in rock exposures worldwide. Tiny glass beads and shocked quartz grains, created under extreme pressures, pepper this layer, offering forensic clues to the impact's magnitude. Each particle etched into sediment binds continents in a shared chronicle of disaster. In contemplating Chicxulub's legacy, we confront both the fragility and resilience of life. The end of the non-avian dinosaurs cleared ecological space for mammals and birds to flourish, ultimately giving rise to the ecosystems we know today. Yet the abruptness of the event, the sheer scale of environmental transformation, reminds us how swiftly Earth can pivot from stability to crisis. The story of the Chicxulub impact resonates more than ancient history. It echoes as a cautionary tale of planetary vulnerability and the indomitable drive of life to endure in new forms. Part 2. Deccan Traps. In western India, the Earth's crust ruptured in a spectacle of fiery upheaval beginning around 66 million years ago. Across an expanse larger than France, vast fissures in the Deccan Plateau spewed torrents of basaltic lava, layer upon layer, accumulating to thicknesses of hundreds of meters. These flood basalt eruptions, pouring out over several 100,000 years, reshaped the land, burying ancient river valleys beneath molten rock seas. From what was once lush forest to barren volcanic plains, the landscape transformed into an alien world of fresh black rock, a tragic prologue to the mass extinction that would follow. The sheer volume of lava, estimated at nearly 1 million cubic kilometers, spewed unimaginable quantities of volcanic gases into the atmosphere. Sulfur dioxide, carbon dioxide, and hydrogen fluoride billowed skyward, forming aerosol clouds in the stratosphere that reflected sunlight and triggered bouts of rapid cooling. Tree ring studies and pollen records reveal that every volcanic pulse sent shockwaves through global climates, with plant communities in India and beyond collapsing under cold snaps and acid rain. This erratic climate, swinging between frigid volcanic winters and greenhouse warming, placed immense stress on dinosaurs accustomed to more stable Mesozoic weather. Local ecosystems endured direct assaults as lava flows consumed riverine habitats and ash-blanketed floodplains. Fossil beds near the Western Ghats contain the last remains of hadrosaurs and titanosaurs, their bones entombed in volcanic detritus that choked water sources and buried feeding grounds. Amphibians, sensitive to water pH, suffered mass mortality when acidic ash dissolved in ponds and streams. Yet in the shadow of destruction, hardy pioneer species, ferns and mosses, colonized the cooled basalt, their spores carried by wind into crevices where soil had yet to form, marking the first stirrings of ecological renewal on barren rock. Beyond India, the Deccan's reach extended to the oceans. Volcanic CO dissolved into seawater, driving ocean acidification that imperiled shell-building plankton and reef communities. Sediment cores from the Indian Ocean show shifts in foraminifera populations, with calcifying species plummeting after major eruptive phases. The collapse of these microorganisms reverberated up the food chain, diminishing fish and marine reptile populations already stressed by the looming asteroid event. In this way, Deccan volcanism preconditioned both land and sea for widespread biotic disruption. Climate models suggest that during peak eruptive phases, global average temperatures swung by as much as 5 degrees Celsius within centuries. This rapid oscillation, cooling from sulfur aerosols followed by greenhouse rebound, confounded the adaptive capacities of many species. Dinosaurs with narrow environmental tolerances found their habitats shifted beyond habitability, forcing migrations that led to overcrowding and heightened competition. The steady pounding of these climatic pulses, repeated over tens of thousands of years, weakened ecosystems long before the final blow from the Chicxulub impact. Intriguingly, the most intense phase of the Deccan eruptions coincides closely with the Cretaceous-Paleogene boundary, suggesting a synergistic effect with the asteroid event. As the world reeled from darkened skies and acid rains, the asteroid's fiery aftermath delivered an onslaught from above: dust-choked atmospheres, global wildfires, and impact winters. The combined stress of prolonged volcanism and sudden cosmic impact created a 1-2 punch, ensuring that few species could adapt to the compounded environmental chaos. Survivors of the Deccan turmoil exhibited remarkable resilience. Small mammals, some of which burrowed into volcanic soils, found refuge underground where temperatures remained more stable. Crocodilians and turtles, amphibious and capable of subsisting on detritus, endured acidified waters and ash-laden air. Fern spores and bacterial mats colonized scorched landscapes, providing rudimentary food webs upon which these pioneer vertebrates depended. In these volcanic refugia, the seeds of post-Cretaceous life took root even as larger species perished. The Deccan traps left an indelible mark on Earth's geology and biology. Today, the gnarled basalt columns and stepped plateaus stand as monuments to the planet's fiery past, their layers recording eruption pulses in volcanic stratigraphy. Fossil pollen, charcoal deposits, and isotopic anomalies within these rocks continue to inform scientists about the timing, intensity, and environmental consequences of this great flood basalt event. Each measurement refines our understanding of how prolonged volcanism interacts with climate systems and living organisms. Ultimately, the story of the Deccan traps reveals that Earth's internal heat can rival the cosmos in shaping life's destiny. These eruptions were neither a singular spectacle nor an isolated catastrophe, but part of a grand tapestry of global change that, alongside an asteroid strike, orchestrated the end of the dinosaur age. Yet from the smoldering basalt fields, life's tenacity shone through: pioneer plants greening black rock, resilient vertebrates carving niches in harsh conditions, and ecosystems poised on the brink of transformation. The Deccan saga reminds us that destruction and creation are two sides of the same volcanic coin, eternally linked in Earth's dynamic story. Part 3. Siberian Traps. The Siberian traps represent one of Earth's most colossal volcanic events, yet its echoes resonate through the Mesozoic as a cautionary prelude to later mass extinctions. Around 252 million years ago, vast fissures in what is now Siberia unleashed flood basalts covering over 2 million square kilometers. Though this predates dinosaurs, its lessons in volcanic magnitude and environmental upheaval presaged the end Cretaceous crises. The sheer volume of lava, estimations range as high as 4 million cubic kilometers, transformed landscapes, obliterated habitats, and saturated the atmosphere with volcanic gases on a scale unrivaled in human memory. Sulfur dioxide from the Siberian eruptions soared into the stratosphere, creating a planet-wide veil of reflective aerosols. Climate modeling suggests sunlight plunges of up to 20% inducing global cooling akin to a volcanic winter. Yet as the aerosols gradually settled, greenhouse gases, carbon dioxide and methane, accumulated to staggering concentrations, driving a runaway greenhouse effect. Temperatures are thought to have spiked by as much as 8–10 degrees Celsius above pre-eruption levels, creating an environmental roller coaster of frigid darkness, followed by searing heat that persisted for hundreds of thousands of years. Marine realms bore a brutal toll. Ocean anoxia spread as temperature-driven stratification blocked oxygen exchange in deeper waters. Sediment cores reveal widespread deposition of organic, rich black shales, a hallmark of oxygen-deprived basins. Marine invertebrates from trilobites to ammonoids vanished in staggering numbers, and fish populations collapsed. Though marine reptiles and early dinosaurs lay in the future, these ancient seas demonstrated how volcanic forcing could dismantle oceanic food webs, a scenario that would replay in miniature after later flood basalt events. On land, ecosystems fractured under acid rain carried by atmospheric currents across continents. Tree ring studies in paleoforests show abrupt growth halts corresponding to acid deposition. Plants crippled by leaf damage and soil acidification could not sustain herbivores, triggering trophic cascades that echoed through Permian tetrapods. The lesson endures: volcanic aerosols and acids can devastate terrestrial vegetation within seasons, imperiling every creature that depends on green matter, a vulnerability keenly felt again in the late Cretaceous. The Siberian traps also spewed vast amounts of methane by igniting coal seams and destabilizing permafrost. Methane, far more potent than CO2 in the short term, amplified greenhouse warming impulses that modern climate projections warn could occur with Arctic thaw. These methane surges melted polar ice, raised sea levels, and supercharged anoxic events. The interplay of volcanic and biogenic greenhouse gases illustrates how feedback loops can accelerate environmental collapse, an ominous parallel to concerns over anthropogenic methane releases today. Despite its timing before dinosaurs, the Siberian saga influenced early Archosaur radiation by clearing ecological space in the aftermath. As ecosystems recovered over millions of years, new groups emerged to exploit vacant niches. The end-Triassic extinction, partly driven by later Central Atlantic magmatic province volcanism, would further reshape life, enabling dinosaurs to dominate terrestrial ecosystems. In this sense, the Siberian traps set the stage for dinosaur ascendancy by exemplifying how extreme volcanism can reset evolutionary trajectories. Geochemical fingerprints link Siberian traps, flows to mercury anomalies, and carbon isotope excursions in global sediments, providing forensic evidence of eruption timing and duration. These markers help paleontologists correlate disparate fossil sites, revealing synchronous extinction pulses across continents. Applied to the late Cretaceous, similar isotopic detective work ties volcanic and impact events to biotic turnover, underscoring the value of Siberian studies in unraveling the mechanics of mass extinction in any era. Modern analogues of the Siberian trap's environmental effects appear in large-scale volcanic eruptions, industrial emissions, and even geoengineering proposals. While no human activity rivals Siberia's basalt outpourings, the principles of aerosol cooling, greenhouse rebound, and ecosystem stress remain relevant. Studying the Siberian record reminds us that Earth's systems can shift abruptly under sustained forcing, offering both warning and perspective on current climate trajectories. In reflecting on the Siberian traps, we recognize that deep-time volcanic cataclysms shaped life's evolutionary path, long before dinosaurs thundered across Pangaea. These ancient flows triggered global crises that reshuffled ecosystems, cleared room for new lineages, and sculpted the biological world that would give rise to dinosaurs and eventually humanity itself. Their legacy endures as both parable and prelude, teaching us that the forces beneath our feet can rival those from the heavens in shaping life on Earth. Part 4. Impact Winter. When the Chicxulub asteroid struck, it did more than obliterate swaths of land and sea. It ushered in an impact winter, a prolonged period of darkness and cold, unlike anything experienced by Earth's ecosystems in tens of millions of years. Fine particles of dust, vaporized rock, and soot from global wildfires soared into the stratosphere, where they mingled to form a light, blocking veil that circled the planet. With sunlight choked off, photosynthesis ground to a halt, triggering a cascade of biological failures as the foundations of food webs collapsed beneath an ashen sky. In the first moments after impact, incandescent ejecta entered the atmosphere, heating and ionizing air columns before raining down as glowing microtectites. These spherules ignited vegetation upon descent, sparking wildfires that consumed forests from North America to India. The resulting plumes of smoke and soot then joined impact dust in the upper atmosphere, with models suggesting that total sunlight reaching the surface dropped by over 90% within days. Even at high noon, the world would have resembled twilight, a dim glow insufficient to sustain the green engines of life. Layered into sediments worldwide is a fine boundary clay packed with shocked quartz and iridium, marks of impact, but also with soot rich in carbon spherules. These telltale particles indicate that wildfires were nearly global in scope. Pollen records from the Hell Creek Formation show a dramatic decline in angiosperm diversity immediately after the impact, replaced by fern spores as pioneer species in a fern spike. Ferns, with their lower light requirements and resilient spores, briefly dominated the charred landscape before succumbing to prolonged darkness. The residence time of aerosols in the stratosphere, months to years, determined the duration of the impact winter. Sulfate aerosols formed from vaporized gypsum and sulfur-bearing rocks reflected sunlight and cooled surface temperatures by an estimated 20 degrees Celsius in some regions. Ocean surface temperatures likewise plunged, disrupting thermohaline circulation and causing marine cold snaps that devastated plankton communities. These microscopic drifters, starved of sunlight, collapsed, unraveling marine food chains from the bottom up and contributing to mass die-offs of fish and marine reptiles. Terrestrial animals fared no better. Herbivorous dinosaurs, dependent on green foliage, perished within months as plants wilted under the smoky gloom. Carnivores followed, their prey dwindling to extinction. Fossil trackways disappear abruptly at the boundary layer, a silent testament to a world where movement stalled and life could not press on. In deeper soils, chemical signatures capture the abrupt shift. Carbon isotopes record reduced photosynthetic activity, while oxygen isotopes in fossil shells record cooler temperatures, corroborating the chilling narrative etched in stone. Surviving specialists found refuge in pockets where light penetrated or food sources persisted. Aquatic organisms in clear, deep lakes may have endured beneath thin, transparent ice, and root-eating insects or tuber-feeding mammals might have subsisted underground. Tiny mammalian ancestors, insulated by fur and able to exploit insects and detritus, navigated the dark months by lowering metabolic rates, an early form of torpor. Such ecological ingenuity highlights that even amid global devastation, micro-refugia offered lifelines for resilient species. The impact winter's legacy extends beyond the immediate die-off. It reshaped Earth's biological future. As skies cleared over a decade or more, pioneering plants recolonized barren soils, starting with hardy ferns and lichens. Mammals and birds, quick to exploit new niches, radiated into forms that would dominate the Cenozoic. In this sense, the impact winter served as both executioner and midwife. It ended one age of giants and gave birth to another era of adaptive innovation. Today's paleoclimatologists decode the impact winter through proxy records, from sediment cores in ancient oceans to tree ring analogues in modern volcanic dust fall. These data refine our understanding of dust residence times, aerosol optical depths, and recovery intervals. By comparing ancient impact winters with modern volcanic events like Tambora or Pinatubo, scientists calibrate models that reveal how small perturbations scale into global climatic upheavals. The parallels underscore how sensitive Earth's systems are to atmospheric particulates. The story of the impact winter warns of the fragility of Earth's climate, biosphere balance. In an instant, extraterrestrial intervention plunged the planet into darkness, demonstrating that even robust ecosystems can collapse when sunlight is withheld. Yet from this abyss rose a transformed world, teeming with new life. The impact winter remains one of nature's most dramatic reset buttons, an epochal event that reminds us both of the destructive power of celestial collisions and of life's extraordinary capacity to rebound. Part 5. Volcanic Winter. When vast flood basalts erupt over millennia, the atmosphere can transform into a chill furnace, plunging Earth into extended bouts of volcanic winter. Unlike the rapid darkness of an impact winter, volcanic winter unfolds in pulses as sulfur dioxide and ash from successive eruptions inject into the stratosphere. These particles reflect sunlight back into space, cooling surface temperatures by several degrees Celsius over decades. Such cooling events challenge ecosystems accustomed to stable climates, especially during critical periods of dinosaur evolution and radiation. The mechanics of volcanic winter hinge on aerosol chemistry. Explosive eruptions, whether from Siberia's traps or other large igneous provinces, vaporize sulfur-rich rocks, producing sulfur dioxide gas. Once lofted above the troposphere, this gas forms sulfate aerosols that scatter incoming solar radiation. Unlike ground-based ash, which settles quickly, these aerosols can reside in the stratosphere for years, maintaining a reflective cap. Climate models indicate that a sustained volcanic winter could reduce global mean temperatures by up to 5 degrees Celsius, enough to shorten growing seasons and starve primary producers. Evidence for Mesozoic volcanic winters lies hidden in fossil plant records. In regions downwind of major traps, paleobotanical studies reveal layers of stunted growth and abrupt shifts in species composition. Conifer forests give way to stress-tolerant ferns and horsetails, indicating ecosystems struggling under diminished sunlight and acid rain. Fine laminae in sedimentary rocks, microscopic ash layers alternating with organic sediments, record eruption pulses roughly every few thousand years, each corresponding to a cold spell in the fossil tree ring data. Marine realms also felt the chill. Cooler surface waters slowed evaporation, weakening monsoon systems and altering oceanic circulation patterns. The resulting stratification trapped nutrients and oxygen, leading to local anoxia in coastal upwelling zones, deadly conditions for ammonites, belemnites, and marine reptiles. Isotopic analyses of fossil shells from these epochs reveal negative oxygen isotope excursions, a signature of cooler seawater temperatures during volcanic winter episodes. Animal populations struggled under these repeated cold snaps. Herbivorous dinosaurs, in particular, faced dwindling forage as plant growth stalled. Trackway sites for hadrosaurs and ceratopsians show congregation in sheltered valleys, suggesting migratory detours around highlands where snowfall and frost made vegetation scarce. Footprint densities drop sharply during cold intervals, implying mass mortality or forced relocation to equatorial refugia. Predator numbers in turn plunged as prey vanished, leading to cascading extinctions among theropods reliant on large herbivore populations. In periods between volcanic pulses, greenhouse gases, carbon dioxide and methane from degassing basalts and peat combustion accumulated, triggering rebound warming that could exceed pre-eruption temperatures. This rapid climate whiplash imposed metabolic stress on temperature-sensitive organisms. Amphibians faced desiccation in hotter summers, while reptiles risking heat stroke in exposed habitats. Sea turtles struggled with nesting as coastal sands overheated. Thus, survivors of one cold phase confronted blistering heat in the next, shrinking the window of ecological stability crucial for reproduction and growth. Yet volcanic winters also fostered remarkable evolutionary experiments. Mammal ancestors, small and thermally flexible, exploited underground burrows where temperatures remained moderate. Their endothermy provided advantage over ectothermic reptiles during cold spells. In flora, certain cycads and seed ferns developed antifreeze-like compounds in their tissues, allowing them to photosynthesize at lower temperatures. These physiological innovations seeded lineages that would thrive in the cooler Paleogene. Modern parallels emerge in the study of large volcanic eruptions like Mount Tambora's in 1815, which ushered in the year without a summer. Crops failed, livestock starved, and famine spread across Europe and North America. These historical snapshots, though brief compared to flood basalt timescales, underscore how even a single eruption can precipitate global hardships. Extrapolate such effects across millions of years of repeated basalt flows, and the potential for sustained biological upheaval becomes clear. The story of volcanic winter reminds us that Earth's internal forces rival celestial impacts in their capacity to alter climates and life. Flood basalt provinces like the Deccan and Siberian traps serve as reminders that prolonged volcanic activity can suffocate sunlight, chill the planet, and upend ecosystems. Yet from these trials emerged resilient survivors, mammals, birds, and specialized plants that capitalized on new niches. In the interplay of fire and frost forged by volcanic winter, life's resilience shines through, adapting and rebounding even as the skies turn dark. Part 6. Climate Shift. In the wake of the asteroid's impact and the great volcanic eruptions, Earth's climate careens through extremes, reshaping ecosystems in ways both subtle and savage. Atmospheric dust and aerosols first plunged the planet into weeks of near darkness and intense cooling. Once those particulates settled, a rapid rebound unfolded as greenhouse gases, released by wildfires, vaporized sediments, and flood basalts, accumulated in the atmosphere. This oscillation from frigid darkness to greenhouse heat created a climate roller coaster that challenged life at every turn, driving evolutionary experiments in resilience. During the coldest phase, surface temperatures dipped by as much as 15 degrees Celsius. In high latitudes, winter-like conditions extended into summers, with frost occasionally settling on leaves in regions once tropically warm. Paleobotanical records reveal stunted growth rings in fossilized wood and sudden shifts from leafy canopy species to cold, tolerant ferns and horsetails. Equatorial regions, too, felt the chill. Correspondingly stressed plant assemblages and pollen spectra indicate that dinosaurs, accustomed to lush jungles, faced an unprecedented season of sun deprivation. As greenhouse gases mounted, Earth's thermostat swung in the opposite direction. Carbon dioxide concentrations may have doubled within centuries, inducing a rapid warming phase that pushed global temperatures above pre-impact baselines. This sudden heat spike triggered expansion of arid zones and drought stress in inland habitats, while coastal wetlands became sweltering marshlands. The fossil record shows desiccation cracks in once moist sediments and calicae formations in paleosols, testifying to periods of extreme aridity that parched soils and drove animals to seek refuge near dwindling water sources. Ocean currents, too, felt the turbulence. Cooler surface waters from volcanic winters altered thermohaline circulation, slowing nutrient upwelling along continental shelves. As heat returned, stratification intensified. Warm, fresh surface layers overlaid cooler, saltier depths, starving deep waters of oxygen. Benthic bottom-dwelling creatures suffered mass die-offs, recorded in sediment layers rich in organic matter and perit. Meanwhile, plankton communities shifted composition dramatically, favoring warm water species during greenhouse phases and cold water types during cooldowns, revealing a marine drama of adaptation and collapse. These climate extremes forced dinosaurs into migratory crusades, unlike any before. Hadrosaurs in western North America left their customary floodplain grazing grounds to trek tens of kilometers northward, following the brief windows of plant growth. Polar dinosaurs, accustomed to seasonal darkness, may have retreated to equatorial corridors or hibernated in burrows, though true hibernation in dinosaurs remains debated. The fossil trackways showing abrupt shifts in travel direction hint at desperate searches for habitable oases amid a world of shifting climates. Isotope analyses of tooth enamel and bone phosphate carve out a picture of life under climatic whiplash. Oxygen isotopes record temperature swings, while carbon isotopes capture shifts in plant productivity and food sources. In some dinosaur groups, we see correspondingly flexible diets, as herbivores pivoted from cycads to ferns to flowering plants, depending on which food source endured the stress pulses. Such dietary agility may have determined which lineages ultimately survived the end Cretaceous upheavals. Even within species, climate stress left its mark on growth patterns. Bone histology reveals alternating fast and slow growth zones corresponding to warm, wet intervals and cold, dry spells respectively. In certain sauropods, individuals reached adulthood in as few as 10 years during warm phases, while cooler periods stretched maturation to 15 or more. An evolutionary gamble, balancing rapid size gain against resource scarcity. These growth records speak to the intimate entanglement of climate and life history strategies across Mesozoic taxa. Amid destabilized habitats, refugia became lifelines. Island mountain ranges, coastal swamps and deep river valleys offered microclimates buffered from the worst extremes, supporting pockets of survivors in an otherwise hostile world. Mammalian ancestors, small and burrow-dwelling, thrived in these niches, exploiting insect prey and underground plant roots shielded from surface vicissitudes. These refugia seeded the renaissance of life in the Paleogene, as climates stabilized and ecosystems rebounded from the aftershocks of global turmoil. The story of the end. Cretaceous climate shift underscores the fragility and resilience of Earth systems. Rapid swings from impact winter to greenhouse peak reveal how tightly life is bound to atmospheric chemistry and temperature. For dinosaurs and their contemporaries, survival demanded flexibility in diet, behavior, and physiology. Qualities echoed today in species coping with anthropogenic climate change. As we probe the ancient record, we glean both warnings and lessons that Earth's climate can pivot swiftly under forcing, yet life's tenacity can endure and adapt across even the harshest transitions. Part 7. Sea level fall. As Earth's climate cooled during the impact winter and subsequent volcanic winters, global sea levels fell dramatically, reshaping coastlines and reshuffling habitats. A drop of up to 100 meters exposed vast continental shelves, transforming shallow epicontinental seas into dry land. This sudden regression erased nursery grounds for marine reptiles and fish, while coastal forests and swamps, once teeming with dinosaurs, collapsed without their brackish lifelines. In a world where the interface between land and sea teemed with life, the retreat of water proved as lethal as darkness or frost. The retreating waters carved new landscapes of salt flats and tidal marshes, but these briny wastes offered little refuge for organisms adapted to stable shoreline environments. Ammonites, once populous in shallow seaways, left stranded shells in drying lagoons, fossil collateral of the regression. Fossil beds in what is now North Dakota and Argentina preserve horizons of dried mud cracks and evaporite crystals, attesting to seawater withdrawal and hypersaline stress, as ocean margins baked under an ambiguous sun. For coastal dinosaurs, the vanishing seas spelled the loss of feeding and nesting grounds. Hadrosaurs and ceratopsians that grazed lush estuarine vegetation found themselves on parched plains, where drought-tolerant plants replaced the ferns and cycads they once munched. Trackway evidence reveals abrupt shifts in herd migrations, with footprints suddenly leading inland and uphill as dinosaurs pursued dwindling waterholes. These desperate treks often funneled enormous herds through mountain passes and river gorges, creating ecological bottlenecks where disease and predation thrived. Marine regressions also disrupted sedimentary cycles, throttling nutrient delivery from rivers to coastal zones. River deltas that once pumped silts and organic matter into the sea lay dry, starving nearshore plankton blooms. This bottom-mob collapse echoed through trophic levels, starving filter feeders and their predators, ichthyosaurs and plesiosaurs, unable to adapt to neither freshwater nor deep open ocean, dwindled as their prey vanished. The silhouette of marine reptile skeletons in nearshore outcrops marks the last gasp of these giants, stranded by the pull of retreating tides. The newly exposed continental shelves became arenas for rapid plant colonization, but soil development lagged behind. Pioneer species, lichen-like algae and hardy mosses, took centuries to initiate soil formation on raw substrates. In that time, terrestrial herbivores faced expanded deserts that harbored sparse vegetation, requiring adaptations in diet and dentition. Some duck-billed dinosaurs show tooth, wear patterns consistent with eating tougher, more abrasive plants, suggesting niche shifts forced by sea level-driven habitat loss. Meanwhile, inland basins that formed behind regressing seas collected new lakes, some rich in volcanic nutrients from Deccan or Siberian aerosol fallout. These lakes became refugia for freshwater fish, amphibians and crocodilians, their clear waters buffered from saline intrusions. Fossil fish assemblages in these basins reveal rapid speciation events, a surprising flourish of diversity in the shadow of marine declines, underscoring life's capacity to exploit newly formed habitats, even amid global upheaval. As sea levels fluctuated through the greenhouse rebound, Shorelines oscillated between expansion and contraction in successive pulses. Each re-flooding carried new sediment loads and re-established marine corridors, only to be followed by another fall. For migrating marine and terrestrial species alike, these cycles demanded plasticity in behavior and life history. Some dinosaurs may have timed breeding to coincide with high stands, ensuring water-rich environments for hatchlings, while others exploited low stands to colonize newly emerged plains. Isotopic studies of marine sediments capture these sea level swings in strontium and oxygen ratios, allowing precise correlation with volcanic and impact events. By aligning these geochemical signatures with fossil occurrences, paleontologists reconstruct a timeline where sea level fall both preceded and followed climatic extremes. These data reveal how intertwined sea transgressions and regressions were with the larger tapestry of end Cretaceous crises, each amplifying the stresses on vulnerable species. The sea level fall stands as a powerful reminder that extinction drivers extend beyond floods and fires to include the mere absence of water. When the seas withdrew, the boundaries of life contracted, and species tethered to coasts found no place to go. Yet in the drying world, new landscapes emerged, lakes, basins, and deserts that would later cradle the dawn of the Cenozoic. In the interplay of water and land, sea level fall etched another chapter in the story of dinosaurs' last days, illustrating how shifts in Earth's hydrosphere can reshape life's margins as profoundly as any asteroid or volcano. Part 8. Ocean Anoxia. Across the Cretaceous seas, an invisible killer began to spread, one not born of fire or stone, but of stagnation. Ocean anoxia, the depletion of dissolved oxygen in marine waters, turned entire basins into biological dead zones. In the late Cretaceous, signs of this creeping suffocation appear layered in the deep-sea record as thick bands of black shale, sediment rich in organic matter, formed when decaying marine life sank into oxygen-starved abyssal plains. These layers mark moments when the oceans, once teeming with life, could no longer breathe. What sparked this slow drowning of the seas is still debated. One likely catalyst was the vast pulse of nutrients flushed into the oceans from the Deccan traps and eroding volcanic highlands. As phosphorus and iron washed in, massive algal blooms exploded across the surface. When these blooms died, their remains drifted downward, feeding a surge of microbial activity that consumed the available oxygen. In this microbial frenzy, deep waters became uninhabitable, and the rich diversity of bottom-dwelling life, ammonites, bivalves, crustaceans, was decimated. Once oxygen vanished from the depths, something worse began to accumulate: hydrogen sulfide, a poisonous gas produced by bacteria thriving in anoxic conditions. In certain layers of Cretaceous rock, sulfur isotopes hint at episodes when this gas not only saturated the ocean floor, but may have even reached the surface, poisoning marine and coastal ecosystems alike. If hydrogen sulfide breached the atmosphere, it could have also eroded the ozone layer, exposing life on land to lethal doses of ultraviolet radiation. The sea's quiet decay had ripple effects that extended into the skies above. Microscopic fossils called foraminifera offer a chilling view into these suffocation events. In periods of healthy ocean circulation, their shells are diverse and plentiful, but in anoxic intervals, diversity crashes, replaced by a few hardy species adapted to low oxygen environments. Entire families vanish from the fossil record, victims of a chemistry turned hostile. The same pattern appears in mollusks and plankton, all caught in a domino effect as food webs collapsed from the bottom up. Coral reefs, long-standing centers of biodiversity, fared no better. As Anoxia advanced, the balance of the seas tipped. Warmer surface waters and sluggish deep currents reduced mixing, and with oxygen failing to reach lower depths, reef ecosystems began to rot from the inside. Coral growth slowed, fish populations dwindled, and predators lost their prey. Reef limestone layers become patchy or absent altogether in the geologic record during these times. A ghostly absence where once vibrant marine cities stood. Interestingly, some species appear to have flourished in these hostile seas. Certain microbes and sulfur-loving archaea bloomed in the sulfurous darkness, forming thick microbial mats on the seafloor. Even some fish, like the deep-dwelling Enchidus, often called the saber-toothed herring, appear to have survived in stratified waters, possibly by exploiting isolated pockets of oxygen or adapting their metabolism. But these survivors were the exception. The vast majority of marine life perished, as if the oceans themselves had turned their back on their oldest inhabitants. The speed of anoxic events varied. Some unfolded over tens of thousands of years, others in as little as a few centuries, depending on temperature shifts and tectonic triggers. The volcanic outpourings of the Deccan traps, along with elevated CO half levels and acid rain, may have amplified ocean stratification, keeping surface and deep waters from mixing properly. Once initiated, Anoxia often fed upon itself, with dead zones expanding in a feedback loop that became almost impossible to reverse. The fossil record preserves eerie scenes of mass mortality, fish stacked atop one another in ancient lake beds, their gills choked by silt and decay, entire layers of ocean sediment devoid of higher life forms, and plankton blooms followed by sudden extinctions. It's a portrait of seas gone silent, once a cradle of life, now a suffocating tomb. The enduring mystery lies in the extent to which ocean anoxia contributed to the mass extinction at the end of the Cretaceous. It may not have lit the match, but it fanned the flames. When Earth's oxygen engines faltered, the consequences echoed far beyond the water's edge. Anoxia robbed the oceans of their most basic resource, breath, and left behind a stark warning in stone. In the patterns of extinction and the chemistry of ancient seas, the legacy of these oxygen-deprived waters lingers. And for those creatures caught between deep waters and an unstable sky, survival became a matter of cruel luck and biological resilience, a final test in a world unraveling from within. Part 9. Acid Rain. When the skies cleared of impact dust and volcanic ash, another invisible scourge descended: acid rain. The Chicxulub impact vaporized vast deposits of sulfur-rich gypsum and anhydrite beneath the crater site, blasting sulfur dioxide into the stratosphere. Simultaneously, the Deccan and other flood basalt eruptions injected further sulfur emissions. These gases combined with atmospheric water vapor to form sulfuric acid aerosols, precipitating as rain that held the power to dissolve leaf cuticles, leach soils, and corrode the shells of freshwater organisms. In the days and weeks after the impact, rainwater pH values may have dropped below 3, comparable to modern industrial acid rain worst-case events. Plants unaccustomed to such acidity suffered rapid leaf tissue damage, visible in the fossil record as sudden declines in leaf cuticle thickness and stomatal density. Pollen grains from early Paleogene sediments bear etching and deformation patterns consistent with acid corrosion, indicating that even the hardy ferns which briefly recolonized scorched soils did so under duress. Acid rain did not confine its assault to vegetation. Freshwater ecosystems, cradles for amphibians, turtles, and certain fish, experienced a sharp decline in water pH that destabilized ionic balances in organisms. The process of osmoregulation faltered as gill and kidney functions failed, leading to mass die-offs preserved in fossil lake beds. Layers of dead fish and tadpoles, their bones scattered in acidic bottom sediments, testify to a watery graveyard where the acid literally ate away at the backbone of freshwater food webs. Soils, once buffered by organic matter and mineral composition, became leached of vital nutrients. Calcium and magnesium, critical for amphibian bone formation and dinosaur eggshell strength, washed away in successive rains. The result was widespread nutrient starvation. Herbivorous dinosaurs struggled to find foliage with sufficient mineral content to sustain bone growth and egg production. Eggshell fragments from late Cretaceous nests show thinning and micro-cracking patterns that align with calcium depletion, hinting at lower hatching success rates during acid bombardment. Even marine shorelines bore brunt of acid rains. Coastal runoff carried acidity into estuaries and mangroves, where oyster reefs and other shellfish faced dissolving shells. As pH fell, calcifying plankton in nearshore waters also declined, reducing primary productivity at the base of marine food chains. Sedimentary isotopes from coastal basins reveal negative carbon shifts, signatures of carbon release from dissolving carbonate shells, painting a picture of coastal ecosystems disintegrating under chemical assault. Acid rain's impact varied regionally. Areas downwind of volcanic centers or the impact plume experienced the most severe pH drops, while remote regions saw diluted effects. Yet the global nature of atmospheric circulation ensured that no continent remained entirely spared. High-latitude forests, previously thought protected by polar isolation, registered sulfuric acid markers in ice cores and sediment traps, underscoring the reach of these toxic showers. Even dinosaur populations in Patagonia likely faced episodic acid stress, their survival hanging on microclimates buffered by local geology. Survival strategies emerged among certain species. Aquatic turtles retreated to alkaline lake bottoms rich in carbonate sediments that neutralized acidity, while amphibians sought refuge under leaf litter or in buffered seeps where pH remained tolerable. Dinosaur species that favored alkaline floodplains rich in limestone bedrock found local relief from acid rains, evidenced by concentrated fossil finds in such areas. These refugia acted as havens, sustaining pockets of life as surrounding landscapes succumbed to chemical erosion. The legacy of acid rain extends beyond the Mesozoic, offering modern parallels in industrial pollution and volcanic eruptions. The end Permian extinction, linked to Siberian traps, also saw acid rain erode soils and decimate forests, demonstrating how repeated volcanic events can chemically poison the biosphere. Today's acid deposition from fossil fuel combustion draws stark comparisons, reminding us that sulfuric compounds in the atmosphere remain potent threats to ecosystems. The acid rains that sealed the fate of dinosaurs continue to teach us about the delicate chemistry linking atmosphere, water, soil, and life. As we trace the acid rain's corrosive path through rocks and fossils, we uncover a story of silent chemical warfare waged against every living organism. Its reach, from the forest canopy to the ocean depths, testifies to how brief flashes of geologic violence can unleash prolonged chemical crises. In the faint etchings on ancient pollen and the hollowed shells in coastal sediments, the whisper of acid rains reminds us that extinction can come not only in fire and ice, but in invisible acid storms that slowly erode the foundations of life. Part 10. Ozone loss. High above the world's final dinosaurs, a delicate shield of ozone once absorbed the sun's most lethal ultraviolet rays, safeguarding life below. But in the violent wake of the Chicxulub impact and the cataclysmic volcanic outpourings of the Deccan traps, this critical barrier was fatally compromised. Billions of tons of chlorine and bromine, unleashed from vaporized marine sediments and volcanic gases, combined with sulfate aerosols to create catalytic reactions that tore holes in the stratospheric ozone layer. Within months to years, regions of the sky saw ozone concentrations plummet by more than 50%, leaving vast swaths of Earth's surface exposed to unfiltered UV radiation in intensities never before encountered by terrestrial and marine organisms. Beneath this thinning shield, dinosaurs and other terrestrial life faced a new, invisible threat. UV radiation penetrates skin and eyes, causing DNA damage, sunburn, and cataracts. Fossilized dinosaur eggs from the latest Cretaceous exhibit shell surfaces etched with microscopic pitting patterns consistent with chemical degradation under intense UV. These pitted shells likely lost their mechanical strength and became more permeable, exposing delicate embryos to desiccation and lethal radiation. Even adult dinosaurs with their scaly hides would have suffered skin lesions and eye damage when venturing into unshaded habitats, driving many to seek refuge under dense canopy, a luxury few ecosystems could sustain during the prolonged environmental crisis. Plants, the bedrock of terrestrial ecosystems, experienced a dramatic decline under UV assault. Chloroplasts, the energy-converting centers of leaves, are highly sensitive to UVB damage. When overexposed, their photosynthetic efficiency plummets. In the sedimentary record, pollen grains from the KBG boundary are found with deformed exons, outer walls scarred by acid and radiation. Surviving flora shifted toward UV-tolerant species, such as certain ferns and gymnosperms capable of producing flavonoid pigments that absorb harmful wavelengths. Yet even these hardy survivors grew more slowly, their reduced productivity echoing up the food chain as herbivorous dinosaurs sifted through ever thinner foliage for sustenance. The oceans, too, bore the brunt of ozone depletion. Phytoplankton near the surface, microscopic photosynthesizers responsible for half of the planet's oxygen production, dwindled as UV-Ben penetrated into the photic zone. Marine sediments from the boundary layer record abrupt declines in coccolithophore abundance, key carbonate shell plankton, whose shells also provided ballast for sinking nutrients. With reduced primary productivity, marine food webs unraveled, zooplankton starved, small fish disappeared, and apex predators from mosasaurs to plesiosaurs found their hunting grounds barren. Even shallow coral reef communities show evidence of UV-induced bleaching and mass mortality, long before the final end, Cretaceous wave of extinctions. Amphibians, reliant on moist environments and sensitive skin, were among the first casualties of intensified UV. Their permeable integuments offered no protection against DNA-damaging rays, and eggs laid in shallow water or on damp ground were exposed to lethal radiation levels. Modern studies reveal that amphibian embryos under high UVB suffer increased mortality and developmental deformities, a fate likely mirrored by their Cretaceous ancestors. Fossil amphibian assemblages vanish abruptly at the boundary, underscoring how ozone collapse severed entire reproductive cycles in a single generation. Insects and other invertebrates, vital pollinators and decomposers, likewise suffered. Many insects rely on UV cues for navigation and mating displays. In the KPG proxy record, spongy layers in fossilized beetle elytra hint at UV-induced shell damage. Pollination networks frayed as pollinator populations crashed, reducing seed set in angiosperms at a critical juncture when plant communities were already stressed by darkness, acid rain, and climate swings. The breakdown of these mutualistic relationships hastened the collapse of flowering plants, which in turn deprived herbivores of diverse food sources. Only species with behavioral or physiological UV defenses survived. Burrowing animals such as early mammals avoided the worst of the radiation by remaining underground during daylight. Nocturnal behaviors extended, and pigmentation changes, such as darker skin or fur, may have offered some UV screening. Aquatic reptiles that dove beneath the surface found respite in water's natural UV filter, though shallow dwellers remained at risk. These refugia became crucibles of survival, preserving the lineages that would seed post-Cretaceous recovery. Geochemical evidence of ozone loss emerges in trace markers across boundary sediments. Sudden spikes in nitrate concentrations, produced when excess UV catalyzed nitrogen oxide formation in the atmosphere, appear in globally distributed clay layers. Similarly, certain biomarkers in ancient organic matter indicate UV stress proteins synthesized by surviving microbes and algae. These chemical signatures, like hidden messages in the geological record, confirm a transient but profound opening in Earth's protective armor. The saga of ozone loss highlights an often overlooked dimension of mass extinction, that the sky itself can become a predator. As dunes of dust and towering plumes of ash cleared, the renewed sun burned not with life-giving warmth, but with lethal radiation. In the scorched, acidic and UV-pierced world that followed, only the most adaptable and shielded species endured. The breach in the ozone layer stands as a stark lesson that life's delicate balance relies on fragile atmospheric chemistry, and when that balance is disrupted, extinction can come not only from fires and tsunamis, but from the very rays of the sun once thought to sustain us. Part 11. Dust Veil. When the Chicxulub asteroid struck, it ripped a vast plume of pulverized rock and soot high into the stratosphere, where global winds spread it into a nearly planet-encircling veil of dust. These microscopic spherules, superheated to incandescent temperatures upon RAV entry, rained back down as glowing pellets, igniting surface fires and injecting even more soot into the air. The combined fallout of impact ejector and wildfire smoke blocked as much as 70% of incoming sunlight, turning noon into perpetual dusk for months. In the pale, filtered light, Earth's familiar rhythms of day and night were replaced by an eerie, endless twilight that suffocated photosynthesis and shattered ecological stability worldwide. Under the dust veil, land and sea surface temperatures plunged by up to 15 degrees. Fossil lakes in western North America exhibit ice-resp textures bottomed into formerly temperate sediments, recording freeze events in locales once too warm to sustain ice. Meanwhile, oxygen isotope shifts in deep sea foraminifera indicate rapid cooling of ocean surfaces. Terrestrial plants, starved of light, halted growth. Tree ring analyses from boundary layer wood reveal missing or ultra-narrow rings, evidence that some growing seasons produced virtually no new tissue. In tropical rainforests, multi-story canopies collapsed as upper leaves died, leaving lower layers unable to compensate, and entire woodlands fell silent. Ancient soils became repositories of fine dust. With rainfall severely diminished by atmospheric blockage, particulates remained airborne or settled, only slowly, abrasive and unremitting. Dinosaurs inhaled this dust, lodging minute particles deep in their lungs. Paleopathological studies of boundary layer ribs reveal healed lesions consistent with chronic respiratory distress and infection. Smaller vertebrates, such as mammals and amphibians, suffered bronchial collapse or renal damage as dust clogged delicate tissues. Thus, the dust veil not only starved ecosystems of light, but choked the very breaths of survivors. Marine ecosystems fared no better. As sunlight waned, phytoplankton blooms collapsed, robbing zooplankton of their food source and causing a bottom-up starvation across ocean food webs. Plankton fossils in boundary sediments show abrupt declines in diversity and abundance, followed by layers rich in organic detritus, testament to mass plankton die-offs. Beneath the surface, fish, marine reptiles, and cephalopods faced dwindling prey and chilling waters. The silent oceans, once teeming with life, became spaces of spectral decline, marked by the absence of their former giants. When rain finally returned, weak and acidic from residual sulfur and nitrogen aerosols, it washed dust into lakes and rivers, further impairing aquatic life. Sediment cores reveal thick layers of silt and ash, blanketing stream beds, smothering benthic invertebrates and clogging fish gills. Freshwater turtles and amphibians reliant on gill and skin respiration could not cope with the combined acidity and sediment load, and their fossilized remains cluster in these toxic deltas. Estuaries where land and sea merge became chemical battlegrounds, their delicate salinity balance ruptured as acids and particulates washed in from scorched continents. As the dust veil gradually thinned over a year or more, a subtle green tinge appeared on coastlines where photosynthetic bacteria and hardy algae recolonized sunlit shallows. But this resurgence was fragile. Nutrient pulses from volcanic and wildfire ash fueled massive microbial blooms that upon decay consumed oxygen and spawned hypoxic dead zones. Metallic nodules and laminated black shales in post-boundary strata mark these anoxic episodes, emphasizing how recovery from the dust veil was immediately followed by new environmental crises that further hindered ecosystem rebound. In terrestrial refugia, deep caves, sheltered valleys, and high-altitude plateaus, some plant and animal life escaped the worst of the dust. These microclimates, cooled yet illuminated by scattered sunlight, allowed pockets of ferns, cycads, and early flowering plants to persist. Small mammals and reptiles found permanent homes in subterranean burrows, shielded from dust and cold. Such refugia form the first chapters of post-impact recovery stories, where life's tenacity flickered against the backdrop of a world struggling to reignite its biological engines. The dust veil of the end Cretaceous serves as a stark reminder that even invisible, fine particulate events can devastate life on a global scale. Modern parallels from volcanic eruptions to potential nuclear winter scenarios reflect the same physics. Particles in the stratosphere block sunlight, collapse food chains, and impose multi-year climatic stress. In studying the KBG dust veil, we confront the fragile window through which sunlight nourishes life and the catastrophic consequences when that window shutters abruptly. As we piece together this ancient twilight, we witness how profoundly the sky itself can become an agent of extinction. Part 12. Multiple Impacts. In the tumultuous minutes following the Chicxulub collision, Earth did not suffer a lone blow. Geological evidence points to a spate of secondary impacts scattered across the globe, creating a sinister chain reaction of craters that compounded the devastation. In Ukraine, the Baltish crater, roughly 24 kilometers wide, formed almost simultaneously, ejecting its own veil of dust and gas into the atmosphere. Off Canada's coast, the smaller but still formidable East Barrow Basin crater further shredded ecosystems. These multiple impacts ensured that no corner of the planet escaped the aftershocks of cosmic violence. Each new crater injected fresh plumes of vaporized rock into the stratosphere, amplifying the global dust veil and extending the period of darkness. The cumulative effect of overlapping ejecta clouds prevented sunlight from reaching the surface for years, exacerbating the collapse of photosynthesis already under siege from volcanic aerosols. In regions downwind of multiple impact sites, fossil records reveal even thicker boundary layers of spherules and microtectites, hinting at localized supernights where darkness was absolute and life flickered under a permanent lunar glow. Beyond the atmospheric blackout, seismic waves from the initial impact rippled through Earth's crust, triggering landslides and secondary impacts in distant basins. In North Dakota's Hell Creek Formation, layers of slumped sediment called seismites testify to ground shaking that felled trees and reshaped river channels. These ground tremors, reverberating for hours, would have thrown dinosaurs off balance, fractured eggs, and collapsed burrows. The simultaneous shock of secondary impacts added unpredictable pulses of violence, fracturing habitats already fractious from fire and winter. Coastal regions bore the brunt of cascading tsunamis from multiple impact points. While the Chicxulub sea waves raced across the Gulf of Mexico, secondary craters off the eastern seaboard and in Arctic shelves generated their own deluges. In New Jersey's coastal plain, sedimentary slugs of sand contain marine microfossils far inland, evidence of waves that washed over barrier islands and estuaries. Marine reptiles and fish, driven ashore by triple-threat tsunamis, met their demise in tangled mass mortality layers, their bones strewn in a chaotic testament to oceanic fury. The overlapping environmental insults of dust, acid rain, and seismic shock waves pushed ecosystems into a state of compound stress. Fresh, acid-laden rain from each impact site washed into rivers and lakes, exacerbating freshwater die-offs of amphibians and turtles struggling with acidified waters. Depleted ozone layers worsened under repeated injections of chlorine from vaporized marine carbonates, intensifying UVB exposure with each secondary plume. Dinosaurs that might have weathered a single insult found no respite in a planet subjected to relentless cosmic bombardment. Yet the phenomenon of multiple impacts remains shrouded in mystery. Dating precision for smaller craters carries uncertainties of tens of thousands of years, leaving open questions about whether these impacts synchronized exactly with Chicxulub or formed a more protracted sequence. If they followed within centuries, their compounding aerosols could have created pulses of climatic collapse, a cyclic impact winter that repeatedly smothered recovering life. In a geological blink, Earth endured a barrage of celestial projectiles, each echoing the first in destructive power. Modern models of impact clustering demonstrate how debris ejected by a primary collision can return as secondary projectiles, carving multi-kilometer craters over thousands of kilometers. The Chicxulub event likely spawned such RIS impacts, showering areas far from the Yucatan with smaller but still lethal ejecta. In this light, the notion of Earth as victim of a single asteroid strike fades, replaced by an understanding of a domino effect, one cosmic blow triggering a cascade of impacts that scoured continents and seas alike. In the paleontological record, multiple impacts amplify the narrative of mass extinction. Instead of a singular moment of crisis, we see a crescendo of disasters: impact winter, acid rain, tsunami, shock waves, each intensifying the next. Fossil assemblages near presumed secondary crater sites exhibit stark pulses of extinction and recovery, indicating that life in the latest Cretaceous navigated a perilous gauntlet of overlapping catastrophes. Those few survivors, mammals nestled in burrows, crocodilians in deep ponds, were the lucky few who weathered not one but many celestial storms. The story of multiple impacts reminds us that asteroids do not always strike alone. The cosmos can deliver several blows in rapid succession. As we study craters from the KBG boundary and beyond, each new discovery reframes our understanding of mass extinction mechanics. In this dance of death, Earth's resilience was tested again and again, and only the most adaptable lineages emerged to build the vibrant world that followed. The echoes of those multiple impacts linger in every boundary layer, a symphony of destruction that reshaped life's destiny. Part 13. Gamma-ray burst. Imagine a titanic flash of energy tearing across the galaxy, its origin a collapsing massive star or merging neutron stars billions of light-years away. This gamma-ray burst GRB, focused into a narrow jet, sweeps past Earth's orbit unnoticed by dinosaurs but lethal nonetheless. In seconds, Earth's upper atmosphere is bombarded by gamma photons that break molecular bonds in nitrogen and oxygen, initiating a cascade of chemical reactions. The once stable ozone layer shatters, unleashing ultraviolet radiation in quantities unparalleled even by acid rain or impact dust. Though no physical crater marks a GRB's passage, its invisible blast leaves scars in atmospheric chemistry and biological survival. Within minutes of the GRB's arrival, nitrogen molecules dissociate under gamma bombardment, forming nitric oxide and nitrogen dioxide. These reactive species catalytically destroy ozone at rates far exceeding volcanic or impact-induced depletion. Models suggest that a sufficiently close GRB, within a few thousand light-years, could decimate over 50% of the ozone layer in mere hours. Without this protective shield, UV rays from the sun irradiate the surface with intensities that fry exposed skin and eyes, sterilize pond surfaces, and disrupt the delicate photosynthetic machinery of plants and phytoplankton. For terrestrial ecosystems, the sudden onset of extreme UV exposure would trigger a mass die-off at multiple trophic levels. Plant spores and pollen grains found in boundary sediments exhibit UV etching patterns consistent with sustained high-energy radiation, revealing a pulse of biological stress that cannot be solely attributed to dust or acid. Insect reproductive cycles collapse under UV-damaged eggs, amphibian larval mortality soars, and dinosaur hatchlings, vulnerable in their uncovered nests, succumb to radiation-induced developmental failures. Adult dinosaurs, though shielded by scales, suffer eye cataracts and skin lesions, impairing foraging and predator avoidance in an already battered world. Marine life too falls victim to the burst's legacy. Phytoplankton at the ocean's surface, the foundation of marine food webs, absorb UVB and die in droves, leaving behind vast plankton deserts. Satellite models of modern oceanic UV exposure depict how plankton productivity can crash by over 80% when ozone thins. In the wake of a GRB, entire basins could become biological wastelands. Fish larvae and coral polyps, highly sensitive to UV, vanish, and the ripple effects starve higher predators from fish to giant plesiosaurs. The oceans, once deep reservoirs of resilience, become arenas of silent extinction. Beyond immediate radiation, GRBs inject large amounts of nitrogen oxides into the stratosphere, leading to acid rain that compounds the impact of ozone loss. Rainwater with pH values below 4 washes across continents, corroding plant tissues and leaching soils of essential nutrients. Freshwater systems acidify, endangering amphibians and freshwater fish already vulnerable to UV exposure. In the polar regions where seasonal darkness had once offered glacial shelter, acid deposition and UV permeation converged to create lethal conditions during the return of sunlight. Geochemical traces of ancient GRBs hide in isotopic anomalies. Specific spikes in carbon-14 and beryllium-10 within boundary layers suggest episodes of intense cosmic radiation. Though distinguishing a GRB signature from solar flares or geomagnetic reversals remains challenging, these isotopic markers, alongside sudden shifts in fossil assemblages, hint at a transient but profound cosmic event. Each atom of beryllium-10 embedded in ancient sediments whispers of high-energy interactions in the upper atmosphere, a fingerprint of radiation that bypassed Earth's geomagnetic shield. Survivors of a GRB-induced extinction would require specialized defenses. Burrowing species, shielded beneath meters of soil, escape the worst of UV assault. Aquatic organisms in deep, clear lakes find refuge below the UV penetration depth, their larvae insulated from surface radiation. Certain spores and seeds, with thick protective coats, endure weeks of exposure before germinating in the post-burst world. These ecological refugia, though limited in extent, become the lifeboats in a global ocean of lethal rays. In pondering a GRB's role in the end, Cretaceous saga, we confront a cosmic dimension of extinction often overlooked. Unlike impacts or volcanism, gamma-ray bursts leave no crater, no ash layer easily visible in rock. Their power lies in the silent irradiation of the planet, in the swift severing of atmospheric chemistry that governs life's viability. As astronomers map potential GRB progenitors in our galactic neighborhood, the specter of such a far-flung but devastating event planes into view, a reminder that life on Earth has always navigated a minefield of cosmic hazards. The story of a GRB's devastation underscores the fragility of the biosphere in the face of high-energy radiation. It expands the narrative of mass extinction beyond terrestrial and impact-driven forces to include celestial phenomena that circumvent planetary defenses. In the end, the dinosaurs, and nearly every living thing of their world, faced threats not only from fire and flood, but from the invisible fury of a stellar cataclysm, a gamma-ray blast that may have left Earth's sky unobscured, yet left life behind in catastrophic ruin. Part 14. Supernova Blast. When a massive star reaches the end of its life, it can explode as a supernova, unleashing more energy in a few seconds than the Sun will emit in its entire lifetime. If such a stellar cataclysm occurred within a few dozen light-years of Earth during the late Cretaceous, its radiation and shockwaves could have delivered a lethal double punch to dinosaur-dominated ecosystems. High-energy photons and cosmic rays from the blast would have battered the upper atmosphere, triggering chemical reactions that destroyed ozone, while the shockwaves' charged particles seeded the atmosphere with nitrates and ionized gases. In the first hours after a nearby supernova, intense gamma-ray and X-ray radiation would penetrate the upper atmosphere, dissociating molecular nitrogen N-thice and oxygen O-thice into reactive radicals. These radicals would recombine into nitrogen oxides, No and No-thice, that catalyze ozone destruction. Within days to weeks, models suggest the ozone layer could thin by over 50%, allowing ultraviolet B radiation to flood the surface. Plants and marine phytoplankton, already reeling from dust veils and acid rains, would suffer amplified UVB stress, leading to further collapses in primary productivity across land and sea. Cosmic rays, primarily high-speed protons and atomic nuclei, would arrive in the weeks following the initial photon burst. These charged particles penetrate deep into the stratosphere and troposphere, spawning showers of secondary particles that ionize atmospheric molecules. Increased ionization rates transform atmospheric dynamics. Enhanced cloud nucleation could cool the planet temporarily, while nitrate deposition from cosmic ray-induced NOx would acidify soils and water bodies. The paleoclimate record hints at sudden warming followed by anomalous cooling pulses, signatures that might align with a supernova's complex climatic fingerprint. Isotopic anomalies in boundary layer sediments provide tantalizing clues. Mulvated levels of plutonium-244, a nuclide produced predominantly in supernova nucleosynthesis, have been proposed in sediments near the KBG boundary. Though still debated, these anomalies suggest astrophysical events may have left traces in terrestrial archives. Similarly, spikes in iron-60, another supernova tracer found in deep-sea ferromanganese crusts, point to one or more nearby supernovae around 66 million years ago. Together, these geochemical breadcrumbs hint that our planet was bathed in stellar debris amid the last days of the dinosaurs. Beyond atmospheric chemistry, the blast's radiation would have direct biological effects. High doses of muons, subatomic particles produced when cosmic rays strike the atmosphere, penetrate meters into rock and soil, exposing organisms to deep penetrating radiation. Burrow-dwelling mammals and amphibians, shielded from surface hazards, would still experience cellular damage from muon showers. In modern experiments, even low-dose muon exposure increases mutation rates and cancer risk. In the ancient world, sustained elevated muon fluxes over centuries could have compromised the reproductive viability of long-living dinosaurs. Marine ecosystems faced their own onslaught. Deep-sea organisms, once insulated from surface UV, would encounter increased radiation as ozone thinned and cosmic rays penetrated deeper into the water column. Coral reefs, already battered by acidification and anoxia, would bleach under intensified UV, and benthic fauna would suffer DNA damage from penetrating muons. The confluence of decreased photosynthesis, nutrient upheaval, and direct radiation stress painted a portrait of the oceans as lethal gauntlets, where only the hardiest plankton and microbial mats survived. Terrestrial vertebrates, from sauropods to velociraptors, would encounter a world where midday sunlight scorched rather than nourished. Skin and eye damage became endemic, and behaviors shifted as animals sought shelter during the brightest hours. Nesting species faced bleak prospects. Eggs left in exposed nests received unobstructed UV doses, causing embryonic deformities and mortality. The fossil record's abrupt disappearance of egg-bearing sites and the lack of juvenile remains across multiple dinosaur clades suggest a recruitment failure, no new generation to replace the old. As the supernova's afterglow faded over millennia, Earth's atmosphere slowly healed. Ozone levels recovered as NOx compounds rained out in acid deposition, and cosmic ray flux returned to background solar values. Yet the ecological void left by dying dinosaurs and marine reptiles never closed in the same way. Mammals and birds, having survived by virtue of small size and subterranean refuges, radiated into the empty niches, forging the path that would eventually give rise to humans. The supernova blast hypothesis remains one of the most mysterious and controversial theories for dinosaur extinction. It bridges the cosmic and the terrestrial, weaving a storyline where Earth's destiny was shaped not only by impact and volcanism, but by the death throes of a distant star. In the geological layers of our planet, the remnants of this celestial event, radioactive isotopes and climatic perturbations, invite us to ponder the fragility of life under the gaze of the cosmos, where the final curtain for the dinosaurs may have been drawn by a stellar explosion far beyond our skies. Part 15. Methane Release. Beneath the ancient seas that lapped the shores of late Cretaceous continents lay vast reservoirs of methane hydrates, icy cages of gas locked within ocean sediments. Ordinarily stable under high pressure and cold temperatures, these hydrates held a sleeping giant of greenhouse potential. Yet in the climate upheaval following the Chicxulub impact and the sustained warming from Deccan volcanism, seawater temperatures rose and pressure regimes shifted, threatening the integrity of these methane ice stores. As hydrate stability zones contracted, pockets of methane burst free, bubbling to the surface in a process that could have unleashed gigatons of climate-altering gas almost overnight. Once liberated, methane's coupling with hydrogen sulfide and carbon dioxide likely triggered a rapid greenhouse feedback loop. Methane is over 25 times more potent than CO2 at trapping heat over a century's span, and in the short term its warming potential soars even higher. In a scenario where rising ocean heat prompted significant hydrate dissociation, atmospheric methane levels could have spiked dramatically, driving surface temperatures upward by several degrees Celsius within centuries. This abrupt warming would have reversed the short-term cooling of impact and volcanic winters, subjecting survivors to a second brutal climate swing. Marine ecosystems scrambled under this rapid thermal shock. Coral reefs, already stressed by acidification and anoxia, bleached in warming waters. Tropical plankton communities shifted poleward, leaving nutrient-rich temperate zones to be dominated by opportunistic microbial mats. Fish populations, accustomed to stable thermal niches, found themselves in waters too warm to support larval development, leading to recruitment failures evident in fossil assemblages. Deep-sea communities, insulated from surface perturbations, also suffered as oxygen minimum zones expanded under stratified warming, cutting off habitat corridors for benthic life. Beneath the smothering dust, massive releases of sulfur dioxide from vaporized carbonate rocks and sulfide sediments formed reflective sulfate aerosols. These particles further intensified the darkness, reflecting incoming solar radiation and plunging surface temperatures by more than 10 degrees Celsius. Paleoclimatic models describe an impact winter of extended gloom, where freezing nights alternated with feeble cold days. In the ocean, phytoplankton, tiny architects of the food web, suffered mass die-offs as light penetration dwindled. The resulting marine famine rippled upward through fish, marine reptiles, and seabirds, mirroring the terrestrial starvation gripping herbivorous dinosaurs. When the aerosols finally settled, Earth emerged into a new kind of furnace. Carbon dioxide from wildfires and vaporized sediments had accumulated, trapping heat in a runaway greenhouse effect. Temperatures surged above pre-impact levels, causing acid rain as sulfuric compounds dissolved into precipitation. Rivers and lakes turned acidic, stressing freshwater communities. The climate roller coaster, darkness to cold to scorching heat, subjected surviving organisms to relentless stress, while soils leached nutrients and entire ecosystems sought fragile equilibria in the wake of planetary upheaval. Remarkably, not all life perished. Small mammals, omnivorous birds, crocodilians, turtles, and amphibians found refuge in burrows, dense forests, or aquatic havens. Their ability to consume varied diets, from carrion to seeds and detritus, allowed them to weather the collapse of primary production. Amphibians, with their aquatic larvae, bypassed the need for plant food altogether. These survivors formed the foundation of a new ecological order in the Paleogene, radiating into forms that would come to dominate land and air. The collapse of stabilizing feedbacks magnified the crisis. As warming waters released more methane, the Arctic permafrost, if present in polar Cretaceous regions, could have thawed, adding yet more greenhouse gas to the atmosphere. This cascading release amplified temperature increases, pushing ecosystems past tipping points. The combined assaults of UV radiation, acid rain, dust veils and greenhouse trauma left surviving organisms little room to adapt, leading to a broadening of extinction beyond dinosaurs to encompass myriad other vertebrate and invertebrate lineages. In the Anthropocene era, we recognize echoes of this ancient methane catastrophe in modern concerns over thawing permafrost and deep-sea hydrate instability. As contemporary CO2 emissions warm the planet, the risk of triggering a similar methane feedback loop looms, a stark reminder that Earth's reservoirs of frozen carbon remain potent forces capable of driving rapid climate change. By deciphering the methane release chapter of the End Cretaceous saga, we glean both fascination with deep-time mysteries and cautionary lessons for our own planetary future. The tale of methane release at the end of the dinosaur age reveals a world where hidden stores of greenhouse gas could turn a planet into a hothouse within human lifespans. It underscores that extinction drivers often act in concert: impact volcanism and methane bursts, each amplifying the other's effects. As we listen to the faint gasps of ancient ecosystems in their final chapters, we bear witness to life's vulnerability when the atmosphere itself becomes a furnace, and we are reminded of our fragile stewardship over Earth's climate legacy. Part 16. Carbon Surge. The End Cretaceous world witnessed an unprecedented surge of carbon as massive volcanic eruptions and impact-induced wildfires released vast amounts of carbon dioxide and soot into the atmosphere. Over thousands of years, flood basalts poured out from the Deccan region, trapping carbon in molten rock and sending continuous plumes skyward. At the same time, the Chicxulub collision ignited forests on 2 continents and vaporized hydrocarbons in the crust. This perfect storm of carbon release overwhelmed Earth's natural sinks and drove atmospheric CO2 concentrations to levels not seen since the early Mesozoic. With carbon dioxide accumulating in the air, the greenhouse effect intensified dramatically. Sunlight that once reached the ground was now held aloft by the excess gas, causing global temperatures to climb several degrees Celsius within centuries. The warming trend compounded earlier cooling episodes from dust veils and sulfate aerosols, creating a brutal climate whiplash. Crocodilians and turtles that had survived the dark winter now found themselves in sweltering swamps where heat stress and oxygen depletion in warm water combined to pin life against its physiological limits. Marine chemistry felt the carbon surge as well. Dissolved carbon dioxide shifted the carbonate equilibrium in seawater, making it more acidic. Shell-forming organisms such as foraminifera, coccolithophores and ammonites found their calcification processes collapsing under corrosive water. Sediment records capture a pronounced negative shift in carbon isotopes, reflecting the flood of light carbon into the oceans. Reef communities that had weathered earlier storms now succumbed, and the skeletons of reef builders dissolved before they could fossilize, leaving only ghost reefs of permeable framework. On land, the warming and acidification of rainwater leached nutrients from soils and altered plant communities. Gymnosperms such as conifers held on in upland refuges, but lowlands turned into parched scrub, where only drought-tolerant angiosperms and ferns persisted. Phytolith and pollen records show abrupt vegetation turnovers at the boundary, with forests giving way to sparse fern meadows. Herbivorous dinosaurs dependent on nutrient-rich foliage faced widespread food stress, fueling malnutrition and reduced reproductive rates before they vanished entirely. Isotopic studies of dinosaur bone collagen reveal elevated carbon isotope values consistent with shifts toward carbon dioxide-heavy diets. Tooth enamel in hadrosaurs and ceratopsians records carbon signatures that mirror the atmospheric spike. These data suggest that the last dinosaurs survived on a planet where the very air they breathed altered plant chemistry and reduced the caloric yield of every bite. Their slow decline plays out in the fossil record as shrinking body size and stunted growth rings well before the final extinction pulse. Among survivors, small mammals and birds again leveraged their ecological flexibility to thrive. Mammals exploited underground burrows buffered from temperature extremes and fed on decaying plant matter and insects that persisted in refugia. Birds capable of aerial foraging shifted from large dinosaurs' corridors to coastal cliffs and islands where marine resources remained abundant. Their fossil footprints appear in boundary sediments, testifying to opportunistic lifestyles that capitalized on empty niches and patchy recoveries. Ecosystems on land and sea only began to recover once carbon levels stabilized and natural carbon sinks, such as forests and phytoplankton, re-established themselves. Soil-forming processes on lava flows and ash fields laid down new organic layers over centuries, while early successional plants greedily drew CO2 from the air. In the oceans, surviving algae and cyanobacteria reclaimed surface waters and reoxygenated the deep sea, eventually reviving complex food webs. The carbon surge at the end of the Cretaceous stands as a stark precedent for current anthropogenic emissions. Like the volcanism and impact fires of ancient times, modern fossil fuel combustion injects carbon dioxide into the atmosphere on unprecedented scales. The parallels between two great carbon pulses, separated by millions of years, underscore the fragile balance between life climate and the carbon cycle. They remind us that Earth systems can shift swiftly under carbon stress, and that surviving life must adapt or perish in the face of such global change. As text-to-speech brings these words to life, know that the carbon surge speaks across eons. It warns of runaway warming, ocean acidification, and ecosystem collapse. It illuminates the final chapters of the dinosaurs and the dawn of mammalian dominance. In understanding this ancient carbon crisis, we learn not only the fate of Earth's past, but the stakes we face in our own time. Part 17. Plant Die-Off. In the wake of impact and volcanic cataclysms, the world's greenery began a rapid collapse that reshaped every thriving forest and meadow. Without sunlight from lingering dust and aerosols, photosynthesis stalled and plants wilted across continents. Leaf fossils from boundary strata show abrupt, colorless patterns where chlorophyll would have once flourished. Fern spikes mark the immediate aftermath as pioneering spore-bearing plants briefly carpeted charred soils before even they succumbed to prolonged darkness and relentless acid rains. As seasonal cycles broke down and rainfall acidified soils, plant roots faced chemical assault. Sulfuric and nitric acids from atmospheric reactions leached critical nutrients such as calcium and magnesium and liberated toxic aluminum ions from clays. Under these conditions, young saplings rotted and mature trees shed leaves prematurely. Pollen records from multiple continents reveal sudden declines in conifer and flowering plant varieties and surges in acid-tolerant mosses, only to see these pioneers fade as soil chemistry deteriorated further. The decline in plant cover sapped the very foundation of land ecosystems. Herbivorous dinosaurs faced exponentially increasing travel distances between dwindling food patches as terrain turned to barren expanses. High-density trackways break off abruptly, signaling desperation migrations across parched floodplains. Fossilized stomach contents from the final plant eaters show abrasion indicative of ingesting bark and twigs in a last-ditch effort to extract calories from ever tougher vegetation. Mangrove and swamp forests along coastlines fared no better. Rising ocean acidification and salinity intrusions from disrupted hydrological cycles stressed these brackish habitats until only salt-tolerant grasses remained in scattered marsh islands. Fossilized roots of once sprawling mangrove trees lie entombed alongside shell layers rich in microbial mats that flourished after the great plant die-off. These microbial mats signaled a collapse of complex habitats into simpler systems dominated by opportunistic bacteria and algae. Mountainous regions that initially provided refugia saw plant cover strangled by acidic mist and dust deposition. Alpine flora adapted to thin soils, and high light endured longer yet eventually wilted when snowfields darkened from dust and acid layers impeded meltwater. Sediment cores from glacial lakes record pollen collapse, even at high elevations, signaling that no altitude offered true sanctuary from the global plant die-off. Underneath the soil surface, mycorrhizal networks and root-associated fungi faced starvation as their plant hosts died back. Without plant sugars to fuel their symbiosis, these fungi collapsed and the critical nutrient cycles they maintained ground to a halt. Soil structure eroded rapidly as earthworms and other fauna lost food sources. The once fertile loamy soils turned to sterile dust that blew across desiccated plains, further impeding plant recolonization. In the seas, kelp forests and marine algae likewise suffered from reduced sunlight and acidified waters. Underwater forests that provided shelter and food for fish shrank in depth until only sparse algae patches clung to rocky outcrops. Fish species dependent on these habitats vanished from the fossil record as marine die-off mirrored that on land. Microscopic algae spores and diatom shells record a final bloom season, followed by an abrupt disappearance just above the boundary clay. Yet in this apocalypse, small patches of hardy lichens and cyanobacteria persisted on bare rocks and cooled lava flows. Their simple metabolic pathways and tolerance for extreme conditions allowed them to anchor the first threads of recolonization. These pioneer communities forged tiny pockets of organic matter that would over centuries seed the fragile rebirth of mosses and ferns. Their resilience offers a glimpse of life's capacity to endure, even when the green tapestry of Earth has been shredded. The story of the plant die-off at the end of the Cretaceous is a testament to how central vegetation is to ecological stability. When the green mantle vanished, entire food webs unraveled in a cascading collapse. As we reflect on this deep time crisis, we are reminded that modern ecosystems too rely on intact plant communities. The ancient die-off whispers a warning that swift environmental change can strip the planet of its primary producers in mere years and thrust life into a twilight of survival and sparse recovery. Part 18. Food Chain Collapse. The intricate web of life that sustained dinosaurs and their contemporaries unraveled at the end of the Cretaceous as primary producers vanished and cascaded catastrophes rippled upward through each trophic level. As sunlight dimmed under dust and aerosols, photosynthesis collapsed, silencing the green engines of the world's forests and plains. Herbivorous dinosaurs found themselves starving the lush ferns, cycads, and flowering plants they grazed upon wither left or vanished entirely. Fossilized stomach contents and toothwear patterns reveal desperate dietary shifts. Dinosaur species once content to browse soft foliage began gnawing tougher roots and woody stems, their teeth bearing the marks of abrasive grit and decaying wood. Without abundant plant matter, herbivore populations plummeted, leaving hungry carnivores to roam empty landscapes. With herbivores in decline, small mesopredators first felt the squeeze. These mid-level hunters, raptor types and smaller theropods, relied on plentiful prey such as juvenile dinosaurs and mammals. Trackways in boundary sediments show their sudden disappearance, footprints halting abruptly at the layer where plant fossils fade. Bone beds reveal a last gasp of hunting evidence, fractured limb bones and clustered kill sites, followed by an uncanny silence. As their primary diet vanished, these predators faced starvation or were forced to scavenge carcasses of larger dinosaurs weakened by malnutrition and disease. Scavenging, however, could not sustain them long as carrion quickly depleted, pushing even opportunistic species toward extinction. At the apex of the chain, the largest theropods confronted an ecological abyss. Tyrannosaurus and its kin, once rulers of floodplains and forests, found no prey large enough to satisfy their caloric needs. Skeletal analysis of late Cretaceous tyrannosaurs show evidence of malnutrition, narrowed rib cages, poor bone growth, and tooth breakage from desperate bites on trammeled bone. Their once imposing bite forces became liabilities as they cracked dry megafauna remains in a futile search for marrow fat. The last tyrannosaurs may have resorted to cannibalism in the final years, leaving behind bones with matching tooth marks. Yet even such grim measures could not halt their demise as the prey base evaporated and competitive pressure from scavengers intensified. Marine food chains collapsed in parallel. Phytoplankton bloomed briefly under returning sunlight, but soon succumbed to acidified waters and nutrient starvation. With primary production curtailed, fish populations crashed, and larger marine reptiles, such as mosasaurs and plesiosaurs, vanished from the fossil record. Shell-forming plankton declines are documented in sediment cores, showing abrupt thinning in carbonate deposits. As carbon-based food webs unraveled, scavenging sharks and ray species endured slightly longer by feeding on decomposing carcasses, but these too disappeared when carrion sources dried up. Amphibians and freshwater fish, often overlooked in dinosaur narratives, suffered double jeopardy. Acid rains lowered pH in lakes and rivers, and UV radiation, intensified by ozone loss, mutated eggs and larvae. Their aquatic food webs, built on algae and insect larvae, broke down swiftly. Fossils of amphibian bones cluster in boundary layers, many bearing lesions consistent with acidic stress. Surviving lineages were those that could burrow or estivate underground until conditions improved, a fleeting refuge in a world where food and water quality plummeted. Insects, the silent workforce of decomposition and pollination, collapsed under pesticide-like acid rains and invasive pathogens fueled by warmer post-impact climates. Pollinator losses compounded plant die-offs, ensuring that any surviving flora could not reproduce successfully. Detritivores declined as leaf litter, and wood became chemically hostile and nutrient-poor. With decomposers absent, carcasses and plant debris accumulated, creating an ecosystem choked by unprocessed organic matter that further hindered nutrient cycling. Scavengers, crocodilians, early mammals and birds found temporary sustenance in the remains of larger animals. Fossil sites show clusters of small mammal teeth and bare dog bones near dinosaur skeletons, hinting at communal feasting. These survivors exhibited dietary flexibility, consuming plants, insects and carrion in shifting proportions. Their smaller body size and lower energy demands gave them an edge in a collapsing chain. By diversifying their diets and exploiting micro-habitats, they outlived the giants and laid the groundwork for the new dawn of the Cenozoic. As each link in the food chain snapped, from producers to apex predators, the planet's ecological tapestry tore apart in a tragic symphony of extinction. The end Cretaceous collapse reminds us that the stability of life relies on the continuous flow of energy, from sun to producers to consumers. When that flow is interrupted, the great fabric of biodiversity unravels swiftly. In reckoning with this deep-time tragedy, we gain perspective on the fragility of food webs and the cascading consequences that follow when any one component falters. Part 19. Mammal Competition. In the shadow of the dinosaurs' demise, mammals emerged from their burrows and brush piles into a world of opportunity and challenge. These small nocturnal creatures had weathered the impact winter and volcanic winters by burrowing underground, feeding on insects, seeds and carrion. As the dust veil lifted and plant communities slowly recovered, mammals found themselves at the threshold of ecological niches once dominated by dinosaurs. Yet their ascent was not unopposed. Surviving dinosaurian lineages, crocodilians, turtles and birds, still claimed territory and resources, sparking a fierce competition that would shape the future of terrestrial ecosystems. Mammalian ancestors such as multituberculates and early placentals began to exploit newly available plant resources in recovering forests. Their dentition, complex molars capable of grinding tough plant matter allowed them to nibble on roots, tubers and seeds that herbivorous dinosaurs had once ignored. In floodplain forests regrown on Cretaceous ash and lava fields, these new herbivores encountered ornithischian survivors confined to shrinking refugia. Fossil tooth marks on fossilized wood and seeds show evidence of both groups competing for the same energy-rich food sources. The nimble mammals, with their ability to climb trees and squeeze into narrow burrows, often outmaneuvered larger reptiles, demonstrating that intelligence and agility could rival size and strength in the struggle for survival. Carnivorous and insectivorous mammals likewise pressed into territories left vacant by the extinction of small theropods. Early marsupials and placentals diversified rapidly, adopting diets ranging from insect scavenging to opportunistic predation on lizards, amphibians, and even juvenile dinosaurs. Their jaws, armed with sharp incisors and shearing premolars, delivered precision bites suited for processing both soft and armored prey. In regions where crocodilian populations dwindled under climatic stress, these mammals encountered fewer aquatic predators at riverbanks, allowing them to forage along shorelines and exploit fish and crustaceans exposed by receding waters. The fossil record reveals an uptick in mammalian tooth and jaw adaptations corresponding to these new dietary niches. Social behaviors and reproductive strategies also fueled mammal success in post-Cretaceous landscapes. Many early mammal species exhibited altricial young offspring born underdeveloped but nurtured intensively by parents, enabling rapid population growth despite high juvenile mortality. Meanwhile, surviving dinosaurian species, with life histories tuned to long lifespans and slower reproduction, could not match the boom and bust cycles of opportunistic mammals, Communal nesting sites discovered in Paleocene sediments suggest that some mammal lineages formed social groups to defend burrows and care for young, enhancing survival rates against both predation and environmental extremes. Competition for shelter further intensified as mammals and reptiles vied for burrows, hollow trees and rocky crevices. Burrow entrances lined with small mammal teeth marks appear alongside crocodilian dens at some fossil sites, indicating direct contestation for the same refugia. In regions of volcanic terrain where lava tubes created natural caves, mammal fossils vastly outnumber reptile remains, hinting that these underground sanctuaries favored small endothermic creatures capable of maintaining body temperature in cool darkness. This battle for shelter extended into the arboreal realm, where early tree-climbing mammals exploited palm fronds and conifer needles to avoid ground-bound competitors. Climatic fluctuations in the early Paleogene presented additional challenges. Rapid warming episodes following impact and volcanic winters created humid greenhouse climates where mammalian thermoregulation proved advantageous over ectothermic reptilian competitors. The ability to maintain stable internal temperatures allowed mammals to forage day and night, extending feeding windows well beyond the hours reptiles tolerated. In fossil sites with seasonal growth rings in mammalian bones, wear patterns suggest nearly continuous activity across what had been extended tropical winters, whereas reptile remains cluster in cooler seasons when they bask to gain warmth, revealing contrasting survival strategies. Yet mammal competition was not universally triumphant. In ecosystems dominated by large flighted birds, avian survivors of the dinosaur lineage, mammals faced new aerial predators that hunted by stealth and speed. Bird fossils with talon marks on mammalian skulls testify to deadly encounters in shattered forests. Furthermore, crocodilians that weathered post-extinction upheavals maintained apex predator status in riverine habitats, ambushing mammal herds at watering holes and leaving clustered remains in fossil mudflats. In East Asian basins, crocodilian and mammalian fossils co-occur, suggesting ongoing predator-prey dynamics that balanced mammalian proliferation with reptilian persistence. By the close of the Paleocene, mammalian competition had reshaped terrestrial ecosystems. Ungulate-like hoofed mammals replaced sauropod niches. Early carnivorans patrolled grasslands once grazed by duck-billed dinosaurs, and burrowing rodents aerated soils unturned since the time of ceratopsians. The rise of grasses blooming in the early Cenozoic further favored mammalian herbivores with specialized teeth, cementing their dominance. In this grand contest for life's prizes, mammals leveraged small size, dietary flexibility, social care, and warm-blooded physiology to outcompete and outrun surviving reptilian rivals, marking the dawn of an age ruled by mammals. The mammal competition of the post-Cretaceous world underscores a timeless truth. In nature's theater, victory often belongs not to the largest or fiercest, but to the most adaptable. As dinosaurs faded into memory, our distant ancestors claimed the stage. Their legacy endures in the myriad mammal species that blanket Earth today, each a testament to survival by competition amid the ashes of a vanished world. Part 20. Disease Pandemic. In the turbulent aftermath of impact winter and volcanic winter, habitats shattered and survivors crowded into shrinking refugia, creating fertile grounds for pathogens to spread unchecked. Tiny mammals, once isolated by forests and river systems, now clustered in dense burrow colonies, sharing food and nesting spaces. Their scaled and furry bodies provided perfect hosts for microscopic invaders. As scavenging dinosaurs perished and decaying carcasses accumulated, bacteria and viruses found abundant new niches. Within months, a lethal wave of disease swept across terrestrial and aquatic communities, striking both old-world reptiles and emergent mammalian lineages. These emerging pandemics likely involved a suite of bacterial lung infections and viral fevers, each adapted to exploit the weakened immunity of animals stressed by cold, heat, acid rain, and ultraviolet damage. Respiratory ailments manifested as bone lesions in fossil ribs, indicating chronic lung inflammation among survivors. Amphibians found their permeable skin vulnerable to waterborne pathogens, leading to widespread die-offs in ponds and marshes. Fish fossils in boundary sediments exhibit gill damage, consistent with microbial plankton overgrowth following plant collapse, hinting at a marine disease wave that echoed the terrestrial crisis. In bird descendants of theropod dinosaurs, feather mites and blood parasites found new opportunities as weakened flyers gathered in nesting colonies. Eggshells in fossil nests bear pockmarked surfaces that suggest microbial invasion during incubation, turning what were once protective shells into lethal vectors for embryonic infections. Surviving avians showed signs of bone inflammation in limb joints, a likely result of systemic bacterial infections moving beyond the respiratory tract into the bloodstream and synovial fluids. Herbivorous dinosaurs, already weakened by nutritional stress, became prime targets for gastrointestinal diseases. Pathogens thriving in acidified soils and waters contaminated by runoff likely infected plant matter, making even surviving foliage a source of infection. Fossilized dung in late Cretaceous deposits reveals abnormal spore counts and fungal hyphae interspersed with plant fibers, suggesting that gut microbiomes shifted drastically under disease pressure. In large sauropods, this shift would have impaired digestion, compounding starvation and making recovery impossible. Predatory dinosaurs, forced to scavenge more often as live prey vanished, ingested infected carcasses and became vectors in a deadly feedback loop. Bite marks on conspecific bones from death assemblages suggest that weakened pack members succumbed after group interactions, leaving toothmark patterns that mirror modern studies of rabies and anthrax in wild mammals. Such scavenging transmitted spores and viruses directly into wounds, transforming feeding opportunities into swift transmission pathways. Marine reptiles also fell victim to pandemic waves. Ichthyosaurs and plesiosaurs, reliant on narrow prey sources, experienced secondary infections when their fish stocks collapsed. Wounds from hunting battles provided entry points for waterborne bacteria. Fossils of mosasaurs show lesions on vertebrae attributed to septicemia. These infections spread rapidly where carcasses floated in shallow seas, seeding local outbreaks that radiated outward with ocean currents, striking distant coastal habitats. Some small mammals adapted rapidly, evolving immune responses that conferred partial resistance. Bone histology reveals thickened marrow cavities where white blood cells proliferated. Dental remains show accelerated tooth replacement rates, likely to compensate for tooth loss from abscesses and bone erosion in jaw sockets. These adaptations helped certain lineages endure the peak of disease pressure and later radiate into new ecological roles as predators, herbivores and insectivores in the emerging Paleogene world. Plants too faced pandemic pressures from fungal and bacterial pathogens in post-impact soils. Leaf fossils in early Paleogene strata show rust spots and blotches identical to modern fungal infections under humid greenhouse conditions. Root nodules bear evidence of bacterial symbiote collapse that would have reduced nitrogen fixation and further stressed herbivores dependent on leafy fodder. The combined plant pathogen wave and animal disease pandemic formed a double crisis that reshaped the foundations of post-Cretaceous ecosystems. The disease pandemic at the close of the Cretaceous highlights an often overlooked extinction driver that when animals concentrate in cramped habitats under environmental stress, pathogens can spread like wildfire. In the fossil record, we see the marks of infections etched into bones and eggshells, the silent testimony of microscopic foes. As the dinosaurs faded, tiny agents of disease joined impact chaos and volcanic fury in driving one of Earth's greatest biological turnovers, reminding us that the smallest organisms can exert outsized power over the course of life's history. Part 21. Hypoxia Crisis. As the delicate balance of Earth's oceans unraveled after the cataclysmic events at the end of the Cretaceous, vast swaths of seawater became deprived of life, sustaining oxygen in a phenomenon known as ocean hypoxia. This crisis did not unfold in isolation, but was intertwined with global warming from methane release and carbon surge, acid rain, weakening nutrient cycles, and collapsing food chains. Warmer surface temperatures reduced the solubility of oxygen in seawater and inhibited the vertical mixing that typically replenishes deep waters. The result was a suffocating blanket of anoxia spreading from coastal shelves into the open ocean, extinguishing marine life in its silent wake. The first signs of hypoxia appear in the sedimentary record as laminated layers of black shale packed with organic carbon and devoid of benthic fossils. These fine laminations indicate that oxygen levels had fallen so low that bottom-dwelling creatures could not survive to rework the sediments, allowing delicate layers to accumulate undisturbed. In these lifeless zones, only anaerobic bacteria thrived, metabolizing organic matter and producing hydrogen sulfide that further poisoned the waters. Fish and marine reptiles that once patrolled these shelves vanished, leaving behind empty skeletons washed into deeper basins. Coral reefs, reefs being the rainforests of the sea, were among the first to collapse under the hypoxia crisis. As oxygen levels plunged, corals expelled their symbiotic algae and bleached, their calcium carbonate skeletons left behind as ghostly structures. Reef-dependent fish lost both habitat and food sources, driving them to migrate or perish. Fossil reef sections in the Gulf region reveal a sudden break in coral layers at the boundary, replaced by microbialites and stromatolites. A microbial takeover marking the end of complex reef ecosystems. Open ocean dwellers such as ichthyosaurs and plesiosaurs fared no better. Though highly mobile and able to traverse vast distances, they could not escape the expanding dead zones. Deep diving species encountered low oxygen at greater depths, forcing them into shallower waters already depleted of life. Their carcasses settled into oxygen-starved basins, leaving mass mortality assemblages that record the final struggles of these oceanic predators. Tooth marks on some bones suggest opportunistic scavengers fed briefly before hypoxia claimed even the scavengers. Planktonic communities underwent dramatic shifts under hypoxic stress. Photosynthetic algae in surface waters bloomed briefly during greenhouse phases, but died off en masse when nutrients became trapped under stratified layers. Zooplankton populations crashed, removing the link between primary producers and small fish. Fossil records show successive waves of plankton turnover marked by spikes in radioisotopes and organic carbon, indicating repeated cycles of bloom and crash. These cycles mirror modern dead zone events in places like the Gulf of Mexico, but on a global scale. On land, the hypoxia crisis manifested in coastal wetlands and estuaries where saltwater intrusion met freshwater hypoxia. Mangroves and salt marshes dependent on daily tidal flushing experienced oxygen depletion in their root zones. Tree stump fossils in ancient delta systems exhibit root stress patterns and leaf loss consistent with hypoxic soils. Amphibians and freshwater turtles that foraged in these nurseries faced suffocating waters in both brackish and freshwater ponds, exacerbating their battle against acid rain and UV stress. Marine invertebrates from ammonites to belemnites suffered staggering extinctions under hypoxic conditions. Their intricate shell records reveal growth interruptions in boundary layers, indicating that surviving juveniles struggled to calcify shells in low oxygen and acidic waters. Tooth and jaw elements from predatory cephalopods show signs of malformation, suggesting that hypoxia impaired muscle development and shell formation. The disappearance of these taxa removed both prey and predator roles, simplifying marine ecosystems into monocultures of hardy opportunists. Only a few refugia offered respite from the hypoxia crisis. Deep oceanic trenches that tapped into oxygenated currents served as lifeboats for benthic organisms. Hydrothermal vents provided local oases where chemosynthetic bacteria harnessed chemical energy rather than sunlight, sustaining unique communities of tubeworms and clams. These vent ecosystems persisted even as surrounding seas suffocated, demonstrating that life's tenacity can carve out niches in the most inhospitable conditions. The end of the hypoxia crisis began as Earth's temperature stabilized and ocean circulation gradually restored oxygen to the depths. Phytoplankton blooms resumed, but with altered community compositions favoring species tolerant of fluctuating oxygen levels. Fish and marine reptiles that survived in refugia repopulated emerging corridors, while new lineages evolved to exploit the transformed seascape. The hypoxia chapter stands as a testament to how oxygen, the breath of the seas, can vanish and return, reshaping life in every drop of water it touches. Part 22. Saltwater Intrusion. The retreat of vast inland seas and the upheaval of coastal landscapes at the end of the Cretaceous allowed saltwater to penetrate ever further into river deltas, floodplains and lowland forests. As sea levels oscillated under impact winter and greenhouse pulses, saline tides overwhelmed freshwater systems, turning rivers brackish and flooding soils with dissolved salts. Dinosaur nesting grounds and herding pathways along ancient riverbanks became toxic marshes. Fossil trackways that once charted the steady march of hadrosaurs now end abruptly in layers of halite-rich sediment, a stark testament to saltwater's deadly reach. Plants adapted to freshwater soils faced osmotic shock when saltwater rose. Root cells collapsed under the hypertonic pressure of saline groundwater, and 20% of mangrove and freshwater tree fossils in boundary deposits show collapsed xylem structures. In some regions, what had been lush riparian forests transformed into ghost woods of skeletal trunks encrusted with evaporite nodules. Spore and pollen records reveal an influx of salt-tolerant rushes and grasses as they colonized the newly saline flats. Yet, these pioneering communities offered scant nourishment for herbivorous dinosaurs that relied on freshwater plants with low salt content. Aquatic reptiles confronted the double threat of hypoxia and salinity. Freshwater turtles and gavialid crocodilians adapted to brackish conditions only briefly survived as increasingly saline waters intruded into their nesting and feeding grounds. Fossil skulls of turtles from boundary layers show metaplastic bone growth consistent with prolonged exposure to salt stress in kidney tissues. In contrast, marine turtles and saltwater adapted species repopulated newly expanded coastal lagoons, their hatchlings scuttling across shoreline sands once claimed by dinosaur nests. Inland lakes and ponds trapped by regression of the seas experienced fluctuating salinity that swung from freshwater to hypersaline within seasons. Stromatolite laminae in early Paleocene lake beds record algal mats that thrived in salt gradients lethal to most multicellular aquatic life. Fish fossils from these lakes show euryhaline adaptations such as enlarged gill, lamellae and robust kidneys inferred from vertebral bone histology. Yet these specialists could not forestall the ultimate collapse, as acid rain and nutrient starvation compounded salinity stress. Dinosaurs accustomed to foraging in coastal floodplains found retreat routes blocked by advancing saltwater marshes. Ceratopsians and hadrosaurs migrating inland left fossilized bone beds at newly formed salt flats, where they perished from starvation and dehydration. Bone taphonomy reveals desiccation, cracking, and salt crystal infilling in vertebrae. Even large sauropods whose long necks once accessed high tree foliage could not escape. Saltwater killed lowland plants and highland forests lay beyond their migratory range. Saltwater intrusion also affected insect and microfaunal communities, critical to ecosystem recovery. Freshwater insects like dragonflies and mayflies vanished, replaced by salt-tolerant chiromids and brineflies. These shifts are recorded in boundary layer insect wing fossils and head capsules of larval midges. Amphipods and small crustaceans colonized brackish pools, offering the only prey for surviving fish and waterfowl ancestors. The new food chains, though sparse, provided lifeboats for species that could adapt to salinity extremes. Mammalian pioneers exploited the margins of saline intrusion by foraging on the few freshwater springs and subterranean aquifers buffered from salt contamination. Their burrow networks tapped groundwater lenses unaffected by surface salinity and permitted foraging in hypersaline terrains. Fossil burrow casts from early Paleocene sediments lie within layers of gypsum and halite, showing that these small creatures carved out niches where larger vertebrates could not follow. As Earth's climate stabilized and sea levels fell anew, saltwater retreated from the newly formed coastal wetlands and river deltas. Freshwater systems reclaimed valley bottoms, and soils gradually flushed of accumulated salts by renewed rainfall. Early Paleocene plant fossils document a slow return of freshwater taxa in small patches that expanded over millennia. Yet the scars of saltwater intrusion, evaporate layers, salt-stressed fossils, and vanished dinosaur trackways remain etched in the rock record, a reminder that water's chemical nature can turn life's pathways into death traps. The saltwater intrusion crisis, at the end of the Cretaceous, illustrates how a simple change in water chemistry can cascade across ecosystems, driving extinction and shaping recovery. In today's world, salinization of rivers from sea level rise and irrigation practices echoes this ancient catastrophe, warning that the balance of fresh water and salt must be maintained to preserve life's diversity. Part 23. Hydrothermal plumes. Beneath the tumultuous seas scoured by impact tsunamis and volcanic ash, another hidden force stirred, hydrothermal plumes rising from the ocean floor. In the hours after the asteroid's collision, seawater rushed into the fractured crust beneath the Chicxulub crater, heated by residual impact energy and melting rock. This superheated water, enriched with metals and sulfides, surged upward through vents as towering plumes, transforming the surrounding benthic habitat in ways both devastating and strangely generative. The chemistry of these plumes was unlike any before seen in Cretaceous oceans. Temperatures near the vent orifices soared above 300 degrees Celsius, dissolving iron, manganese and silica from the crust. As the plume water ascended into cooler depths, These minerals precipitated, creating shimmering smoke of particulates that spread for kilometers. In modern mid-ocean ridge systems, similar black smokers host chemosynthetic communities. In the immediate aftermath of the impact, however, the hydrothermal discharge likely overwhelmed existing ecosystems, suffocating nearby corals and sponges under layers of metal-rich sediments. Evidence for post-impact hydrothermal activity emerges in boundary clay deposits rich in hydrothermal silica and sulfide minerals. Core samples from the Gulf of Mexico reveal anomalous enrichments of gold, silver, and platinum group elements, metals leached from impact, heated crust, and redeposited by plume fallout. These metallic snowfall layers coincide with the iridium anomaly, suggesting that the hydrothermal pulse occurred within years of the asteroid strike, blanketing the seafloor in a toxic mineral slurry. Marine life beyond the immediate vent fields felt indirect effects. Plume dispersal altered local pH and redox conditions, triggering deadly chemical gradients. Fish gills and the delicate filtering apparatus of bivalves suffered damage from metal ions and sulfide toxicity. Sediment layers show mass mortality horizons where clam and oyster shells accumulated in thick beds, their interiors pocked with corrosion marks. Free living bacteria bloomed in the plume's affected waters, creating bacterial mats that carpeted the ocean floor and formed the first stages of new chemosynthetic communities. Over the following decades, as basalt flows from Deccan volcanism cooled and fractured, hydrothermal systems proliferated along fault lines worldwide. On continental slopes, cold seeps emerged as methane, rich fluids mixed with basalt, heated water, fueling specialized ecosystems of tube worms and gastropods analogous to modern vent fauna. While dinosaurs roamed on land above, their distant kin in the sea contended with shifting oases where life eked out survival in the chemical glow of Earth's molten core. The interplay of impact and volcanism thus catalyzed a global expansion of hydrothermal activity, creating a mosaic of extreme environments. Each vent and seep served as a microcosm of both destruction and renewal. Tubeworm fossils in early Paleogene strata bear mineralized tubes echoing Cretaceous origins, suggesting that these hardy lineages held on through the extinction and seeded new vent communities in its aftermath. In the grand narrative of extinction and rebirth, hydrothermal plumes stand as agents of transformation, hidden beneath crashing waves. They remind us that life's resilience often hinges on unexpected refuges, worlds of heat and toxicity where chemosynthetic organisms flourish in defiance of surface calamities. As modern explorers map deep sea vents, they uncover living analogues of these ancient systems, their shimmering plumes echoing the long-forgotten fires beneath the Cretaceous seas. The Hydrothermal Plumes chapter unveils a lesser-known theme of the end. Cretaceous crisis that beneath the cataclysmic spectacle of impact and volcano, Earth's internal heat forged new habitats, even as it laid old ones to waste. In these obscure depths, life persisted and evolved, linking the fiery depths of our planet to its ever-changing surface tapestry. Part 24. Supervolcano Eruption. In the shadow of the Deccan traps and Chicxulub chaos, another subterranean menace lay in wait. Supervolcanoes capable of ejecting thousands of cubic kilometers of magma in a single cataclysm. These gargantuan eruptions dwarf even the largest historic events and leave calderas hundreds of kilometers across. Evidence suggests that in the waning days of the Cretaceous, one or more supervolcanoes may have roared to life, punctuating the end Cretaceous crisis with explosive force that rivaled the asteroid impact itself. In their fury, They unleashed pyroclastic flows that razed entire landscapes, tore forests from their roots, and blanketed the sky with thick curtains of ash. The initial blast of a supervolcano eruption would have teared away mountainsides, sending plumes of ash and sulfur dioxide into the stratosphere at altitudes exceeding 30 kilometers. Within hours, volcanic ash circled the globe, darkening skies and triggering acid rains. Sulfur aerosols reflected sunlight back into space, cooling surface temperatures by up to 10 degrees Celsius for years. This volcanic winter compounded the impact winter and volcanic winter already gripping the planet, deepening the collapse of photosynthesis and pushing ecosystems to the brink. Ash fall from supervolcanoes can exceed meters in thickness within hundreds of kilometers of the source. Fossil soils in regions corresponding to modern North America and Asia display layers of vitric ash and accretionary lapilli at the KPG boundary. These layers entomb plant roots and burrow networks, preserving in situ trunks and tuberous plants that perished under the weight of ash. As ash accumulated on leaf surfaces, torsion fractures appear in fossil leaf cuticles, evidence that even hardy gymnosperms succumb to rapid burial and chemical abrasion. Beyond immediate burial, ash altered global hydrology. Water bodies clogged with ash became acidic and turbid, killing fish and amphibians. Rivers choked with sediment collapsed into braided channels, altering floodplain dynamics. In wetlands, marsh grasses and cattails struggled under ash mats that prevented seed germination and root respiration. Fossil pollen from boundary sediments lacks marsh plant signatures for millennia, demonstrating the wholesale loss of wetland habitats. Supervolcanoes also injected massive quantities of carbon dioxide into the atmosphere as magma degassed during eruption. This greenhouse pulse followed volcanic winter, creating a rapid swing from freezing to intense warming. Paleosol carbonates record sharp shifts in soil carbon isotope ratios, indicative of elevated CO2. In the aftermath, global temperatures soared above pre-impact baselines, driving thermal stress in survivors already weakened by cold and darkness. This climate whiplash accelerated extinctions among temperature-sensitive genera across latitudes. Regional effects of supervolcanoes varied with proximity and prevailing winds. In high latitudes, acid snowfalls buried tundra and scrub, freezing soils and delaying spring growth by years. Low latitudes faced acid monsoons that leached tropical soils of nutrients, transforming rainforests into nutrient-poor savannas. The contrast in recovery times between latitude bands appears in paleobotanical records. Tropical zones took longer to regenerate closed canopy forests than temperate regions receiving less acid deposition. Despite the devastation, supervolcanoes also forged new mineral landscapes. Fertile volcanic soils rich in phosphorus and potassium formed on ash beds, eventually supporting lush Paleogene forests. Early mammalian herbivores colonized these fertile areas, exploiting nutrient-dense vegetation that rose in ash-enriched soils. Root traces in early Paleocenes reveal deep taproot systems of flowering plants that took advantage of volcanic soils' water retention properties, providing food sources for evolving browsers. The supervolcano eruption hypothesis weaves a complex thread into the end Cretaceous tapestry. While impact and flood basalts dominated headlines, supervolcanoes remind us that Earth's internal forces operate on multiple scales and can converge in time to produce compound crises. Their echoes in ash layers, chemical proxies, and fossilized root balls underscore how multiple volcanic processes, line fissures, caldera collapses, and explosive supereruptions collaborated with extraterrestrial collisions to reshape life on Earth. As modern scientists monitor supervolcanoes like Yellowstone for signs of unrest, the ancient supervolcanoes of the Cretaceous teach us that the boundary between stability and catastrophe can pivot on geological timescales. In understanding their role in the extinction cocktail, we gain insight into how Earth's mantle and crust interact with climate and life, forging moments of profound transformation in our planet's history. Part 25. Solar Flare. In the waning days of the Cretaceous, Earth's sky faced not only the darkness of a dust veil and the hiss of acid rains, but the potential fury of its own star in the form of a massive solar flare. Such an event, erupting from the sun's shifting magnetic fields, can unleash torrents of energetic particles and X-rays that slam into Earth's magnetosphere. If a flare of unprecedented strength struck when the ozone layer was already compromised by impact-induced nitrogen oxides and volcanic sulfur, ultraviolet radiation and charged particles would have streamed unimpeded to the surface, inflicting widespread biological damage in hours rather than years. Plants, already ravaged by darkness, acid rain, and UV exposure, would have suffered a new assault when high-energy solar particles penetrated the thinning ozone. Photosynthesis depends on chloroplasts built to absorb visible light, not withstand bursts of X-rays and extreme UV. Under such bombardment, DNA in chloroplasts and nuclei would have fragmented, triggering mutations or cell death within minutes of exposure. Fossilized leaf cuticles in boundary sediments reveal UV etching patterns more severe than those attributable to ozone loss alone, hinting at moments of extraordinarily intense radiation. In equatorial forests, once dense canopies may have radiated bright death as trees' leaves turned into glowing embers under solar onslaught. Marine phytoplankton, the invisible engines of oceanic primary production, would have felt the flare's wrath as well. These microscopic organisms float near the surface in sunlit waters and rely on delicate photoreceptors to capture light. A sudden surge of X-rays and extreme UV could have penetrated tens of meters, triggering rapid die-offs across broad swaths of ocean. In deep sea cores, spikes of biogenic sediment followed by barren layers may record these catastrophic plankton crashes, where each collapse rippled upward, starving zooplankton, fish larvae, and ultimately the giant mosasaurs and plesiosaurs that fed on them. Terrestrial animals, from small mammals to giant sauropods, stood vulnerable to radiation sickness. Modern studies show that acute radiation doses cause nausea, hair loss, and bone marrow failure in mammals within days. While dinosaur scales offered some shielding, thick skin cannot block high-energy particles. Bone lesions in reptilian fossils sometimes display patterns consistent with radiation-induced cancers, suggesting that solar flare-based radiation may have compounded other stresses, tipping marginal species into extinction. Burrowing animals huddled underground may have avoided the worst, explaining why small mammals emerge as key survivors in the fossil record. A solar flare would also have induced geomagnetic storms, igniting auroral displays at tropical latitudes and triggering electrical currents in the crust. These electromagnetic pulses could have disrupted primitive electrical signaling in early birds and mammals, causing behavioral disorientation at a critical moment when navigation and foraging required precision under dim, polluted skies. The loss of migratory cues and the scramble to find food in a world already stripped of its vegetative armor could explain the sudden disappearance of certain avian and mammalian fossils from locations once teeming with diverse lineages. Atmospheric chemistry itself would have shifted under the flare's influence. Ionization of the upper atmosphere produces nitric oxide, further depleting ozone and creating nitrous acid when combining with water vapor. This secondary acid rain, richer in nitrates, would have washed into soils and waterways, adding to the sulfuric acid already present. Freshwater systems, the last refuges for many amphibians and fish, would have flooded under a cocktail of acids and nitrates, doubling the challenge of surviving in a world where chemical and radiative insults arrived in unrelenting waves. The timing of such a flare remains speculative, but polar ice cores and tree ring data from younger epochs record historical solar storms in nitrate and beryllium anomalies. If a similar event transpired at the Cretaceous-Paleogene boundary, it could help explain the rapidity of extinctions beyond impact and volcanism alone. Sudden radiation pulses might have erased any remaining patchwork refugia where pockets of life clung to existence between other catastrophes. In a single day of cosmic fury, survivors of multiple crises could have faced an insurmountable final barrier to persistence. In contemplating the role of a massive solar flare in the dinosaur extinction mosaic, we glimpse a cosmos where Earth's fate hinges not only on its own internal and external catastrophes, but on the capricious temper of the Sun. This chapter of solar fury underscores that life's sanctuary lies beneath multiple shields, from the atmosphere's gases to planetary magnetic fields, and when those shields falter, extinction can arrive not only in fire and ash, but in invisible rays racing across space. Part 26. Magnetic reversal. Earth's magnetic field, generated by churning molten iron in its outer core, has flipped its polarity many times through deep time. At the end of the Cretaceous, evidence suggests that one of these geomagnetic reversals may have coincided with the mass extinction event. As the field weakened during the reversal, its shielding effect against cosmic radiation and solar wind particles diminished. Increased charged particle flux bombarded the upper atmosphere, stripping away ozone and altering atmospheric chemistry. This atmospheric thinning compounded the stress from impact, winter and volcanic winters, exposing life on the surface to heightened ultraviolet radiation and charged particles that penetrate deep into tissues. When the geomagnetic field destabilizes, the protective magnetosphere contracts. Satellite studies of modern magnetic excursions reveal that radiation levels at ground level can spike by tens of % during low field intervals. In a Cretaceous reversal, with ozone already depleted by nitrogen oxides from impact and volcanic sulfur, organisms faced a triple threat: diminished ozone, elevated UV and intensified cosmic rays. Fossil bone microstructures from late Cretaceous mammals and reptiles sometimes show unusually high densities of repair deposits around cell nuclei, potential biomarkers of radiation damage. These microlations hint at an invisible killer that worked at the cellular level, weakening immune systems and impairing DNA repair, just as ecosystems teetered under multiple other assaults. Marine life, too, felt the subtle but pervasive effects of a weakening magnetic shield. Cosmic rays penetrating the atmosphere produce secondary particles that cascade into the oceans, altering water chemistry through radiolysis of water molecules. This process generates hydrogen peroxide and other reactive oxygen species that can stress planktonic and benthic organisms. The resulting oxidative stress may have contributed to the collapse of key primary producers, diatoms and coccolithophores, as indicated by shifts in organic biomarker ratios in boundary sediments. As the base of the food web faltered, fish and marine reptiles starved or succumbed to combined chemical and radiative insults. Terrestrial plants exposed to increased cosmic UV radiation bore the brunt of this geomagnetic episode. Fossilized leaf cuticles from boundary layers exhibit deep pitting beyond that explained by ozone loss alone. These pits correspond in size to UVB, or cosmic particle interactions at the cellular scale, suggesting that plants suffered radiation burns in addition to acid rain and darkness. Widespread leaf scorch would have accelerated the collapse of forests, reducing shelter and food for herbivorous dinosaurs and early mammals alike. With leaf canopy thinning, ground temperatures fluctuated wildly, further taxing poikilothermic reptiles dependent on ambient warmth. Animals that relied on geomagnetic navigation, such as migratory birds and hatchling sea turtles, would have found their orientation systems scrambled during the reversal. Though true sea turtles evolved after the dinosaurs, similar reptilian lineages may have used magnetic cues for migration or homing to nesting beaches along ancient coastlines. Disoriented migrations could explain taphonomic clusters of reptile and fish remains in unlikely inland or polar deposits, suggesting navigational errors led survivors into ecological traps where they perished in mass mortality events. Small burrowing mammals insulated below ground escaped many surface effects of the reversal but still faced cosmic radiation penetrating meters of rock in the form of muons. Modern measurements show that muons generated in the upper atmosphere can traverse hundreds of meters of rock and soil, depositing ionizing energy in deep burrow chambers. This subsurface radiation exposure could have increased mutation rates in underground-dwelling species, driving rapid evolutionary experiments in reproductive strategy and DNA repair mechanisms. Surviving mammal lineages bear genetic hallmarks of heightened DNA repair gene expression, a legacy of enduring multiple radiation pulses. Geomagnetic reversals also influence climate by modulating atmospheric circulation patterns. Changes in ionization rates affect cloud nucleation processes, potentially altering precipitation patterns and monsoon intensity. Paleoclimate reconstructions around the KPG boundary show anomalous shifts in rainfall belts and drought pulses that cannot be fully explained by volcanic or impact effects alone. These hydrological changes would have reshaped habitats, drying some floodplains and inundating others, forcing mobile species into new migratory routes that may have intersected deadly traps of acid lakes or hypoxic seas. The co-occurrence of magnetic reversal with other extinction drivers underscores the multifaceted nature of the end Cretaceous crisis. No single cataclysm can account for the rapid and widespread collapse of life. Instead, a convergence of impact, volcanism, climate shifts, ozone depletion, and geomagnetic upheaval created a perfect storm from which few lineages could emerge unscathed. The magnetic reversal, though invisible to ancient eyes, left its signature in isotopic anomalies and fossil damage patterns that modern science can decode as part of a grand extinction puzzle. In contemplating the geomagnetic reversal's role, we see that Earth's internal dynamo and cosmic environment jointly influence life's fate. The invisible shield that once guided migrations and protected DNA briefly faltered, adding a cosmic twist to the terrestrial drama of extinction. As the field reversed and eventually recovered, survivors faced a world reshaped by forces from core to crust to sky, a world ready for new rulers of land, sea, and air in the unfolding Cenozoic age. Part 27. Plate Tectonics. Earth's surface is a grand jigsaw of shifting plates, and at the end of the Cretaceous those plates were on the move in ways that reshaped climates, ocean currents, and the very geography dinosaurs called home. India was hurtling northward after splitting from Gondwana, its leading edge ploughing into Eurasia and igniting the Himalayan orogeny. This colossal uplift altered atmospheric circulation, shifting monsoonal patterns and redistributing rainfall from equatorial floodplains to expanding mountain rain shadows. As precipitation belts moved, so did vegetation zones, forcing herbivorous dinosaurs to follow familiar habitats northward or risk dehydration and starvation in newly arid landscapes that once teemed with life. Meanwhile, North America and Eurasia were drawing closer as the North Atlantic Rift widened, deepening the Atlantic Ocean and altering marine gateways between Arctic and Tethys seas. These changing waterways reconfigured ocean currents, impacting heat transport from equator to poles. Cooler high-latitude waters contributed to polar glaciations, challenging cold-intolerant species. Fossil flora from northern Alaska reveal sudden shifts from temperate to near-tundra conditions in the final million years of the Cretaceous, hinting that plate tectonic-driven climate change pushed polar dinosaurs to the edge of their thermal limits even before impact struck. In South America, Africa and Australia, plate motions isolated former connections that had allowed widespread faunal exchanges since the Jurassic. As shallow seaways closed and continents drifted apart, dinosaur populations became increasingly provincial. Endemic lineages blossomed in isolation, but lacked the genetic diversity to adapt when global stresses intensified. When environmental upheavals accelerated, these isolated populations could not migrate to more hospitable regions, accelerating local extinctions. Gondwanan dinosaur clades vanish from the fossil record in lockstep across both South America and Africa, underscoring the fatal consequences of tectonic isolation. Subduction zones bordering the Pacific Rim churned in the late Cretaceous, generating volcanic arcs that spewed tephra and gases into the atmosphere. The Pacific Ring of Fire pulsed with activity, injecting sulfur and ash into jet streams that carried them across continents. Combined with Deccan volcanism and impact ejecta, these volcanic arcs contributed to the global veil that dimmed sunlight. Sediment cores in western North America contain ashes from Alaskan and Japanese eruptions interleaved with boundary layers, indicating that plate-driven volcanism far from the Deccan region also played a supporting role in atmospheric poisoning. The uplift of new mountain ranges created rain shadows and rear-fashioned river systems. As sediments eroded from Andean highlands in South America, they filled westward basins, creating vast inland lakes that served as refugia for fish, turtles, and some small dinosaurs. Conversely, eastern lowlands dried as moisture was trapped on windward slopes. In those new deserts, sauropod footprints vanish abruptly in favor of resilient small mammals and burrowing reptiles. The changing topography forced unprecedented migrations and extinctions, as some species tracked their ancient river corridors, only to find them choked with sediment or cut off by rising mountain barriers. Plate tectonics also influenced coral reef distributions. As seafloors spread and continental shelves shifted, reef habitats contracted or relocated. In the late Cretaceous, the Tethys Sea corridor supported extensive reef complexes that sheltered marine reptiles and invertebrates. When Africa and India drifted north and the Tethys began closing, reef belts fragmented. Fossils of mosasaurs and plesiosaurs tied to reef margins show their disappearance from certain regions corresponds with the loss of these shallow marine habitats, hinting that tectonics drove both emergences and extinctions of apex marine predators. The interplay of plate motions and sea level changes further complicated the picture. Tectonic uplift can lower relative sea levels regionally, exposing continental shelves, while subsidence in other areas deepens epicontinental seas. In Europe, shallow seaways formed and vanished in quick succession, leaving behind sedimentary records of rapid transgressions and regressions. These fleeting seas provided migration routes for marine dinosaurs and flying pterosaurs, only to strand them when waters withdrew. The fossil record in Germany's chalk deposits reveals mass strandings of marine reptiles tied to these tectonic pulses, evoking scenes of creatures trapped on desiccating shelves. In the wake of the asteroid impact, survivors found themselves on a planet with plates continuing their inexorable drift. Mammal lineages that persisted on island, like Refugia, gained new opportunities to radiate across shifting continents. As North America and Eurasia reconnected intermittently, land bridges allowed some mammal groups to expand into formerly dinosaur-dominated realms. These tectonic corridors facilitated the Great Paleogen mammalian radiation, turning former dinosaur strongholds into mammal kingdoms shaped by the very plates that had contributed to the dinosaurs' fall. Plate tectonics reminds us that life's stage is never static. Continents collide, slide, and sink in cycles that outlast individual species. The end of the Cretaceous era was not merely the closing of a day, but the turning of a page in Earth's tectonic diary. In the dance of plates, we see how the ground beneath our feet can shift climates, carve seas, and shepherd life through extinction and rebirth. Plate tectonics served as both sculptor and executioner in the age of dinosaurs, shaping the world that would become ours. Part 28. Pangaea Breakup. The supercontinent Pangaea had already begun its slow fracture by the latest Cretaceous, its lithospheric plates pulling apart like a cracked shell. Rifts opened between landmasses that had long shared flora and fauna, creating new oceans and severing ancient migration routes. In the northern hemisphere, Laurasia separated into North America and Eurasia as the central Atlantic widened. In the south, Gondwana fragmented into Africa, South America, Antarctica, India, and Australia. These shifting continents reshaped coastlines and inland seas, so that what had once been vast floodplains teeming with dinosaurs became isolated islands or submerged continental shelves where only hardy survivors could persist in fragmented habitats. Rising seas flooded rift valleys, cutting inland channels where saltwater intrusion turned freshwater marshes into brackish lagoons. Dinosaurs following rivers for water and food found those paths unpredictably altered by tectonic subsidence. Trackways abruptly end in sedimentary layers rich in marine fossils, testifying to sudden inundation. Herds of hadrosaurs and ceratopsians that once roamed coastal plains vanished from those regions as the waters rose and flooded their nesting grounds in brackish swamps where eggs could not survive high salinity. As continents drifted, ocean currents reorganized. The opening South Atlantic redirected warm equatorial currents toward higher latitudes, warming polar regions while cooling tropics. Fossilized flora in paleobotanical records from Greenland and Siberia reveal tropical plant species persisting far north, long after they died out elsewhere, hinting at milder polar climates created by shifting currents. Polar dinosaurs, once confined to darkness at high latitudes, may have extended their ranges as seas transported heat, poleward reshaping ecological zonation on drifting landmasses. Volcanic arcs formed along newly active plate boundaries, injecting ash and sulfur into the atmosphere. Island arcs and microcontinents sprouted where oceanic plates subducted beneath continental margins. These eruptions enhanced the global dust veil, seeded by asteroid ejecta, threatening photosynthesis in plant communities already stressed by sea level changes. Layers of volcanic ash, interbedded with boundary sediments in western North America and Europe, attest to multiple volcanic pulses coinciding with tectonic rifting, adding another layer of crisis to the end of the age of dinosaurs. Mountain building surged along rift flanks, creating nascent ranges that rerouted river systems and carved rain shadows. In South America, the Proto-Andes uplifted, altering monsoon wind flow and creating arid basins where once lush forests thrived. Fossil soils in the Atacama region date to this uplift era, capturing root traces of drought-resistant ferns and cycads that eked out an existence in drier air. These mountainous refugia offered transitional habitats that only the most adaptable dinosaur lineages could exploit before the final extinction waves swept across the continents. Island isolation driven by fragmentation fueled evolutionary experiments in dwarfism and gigantism. In ancient Eurafrican archipelagos, small sauropodomorphs shrank to size of modern elk to survive on limited island resources, while small theropods on Madagascar grew larger in absence of apex predators. Fossils from these landlocked islands show pronounced changes in bone histology, indicating altered growth rates under resource constraints. Such insular adaptations hint at rapid evolutionary shifts forced by tectonic breakup, even before global extinction pressures peaked. As plate tectonics carved new ocean basins and severed land bridges, the distribution of flowering plants and early mammals shifted dramatically. Pollen records revealed distinct floral provinces emerging on each drifting continent, with flowering plants radiating into newly available niches. Early placental mammals exploited these plant radiations by diversifying herbivorous and omnivorous lineages, adapted to local vegetative assemblages. These adaptive radiations laid the groundwork for the mammalian dominance of the Cenozoic world, even as dinosaurs faded from view. By the very end of the Cretaceous, Pangaea's remnants had rearranged Earth's geography so thoroughly that ancient migratory paths were forever lost. The separation of continents created barriers that prevented rescue migrations when global crises struck. Dinosaurs confined to shrinking land masses could not escape the combined assaults of climate shifts, volcanic winters, and asteroid fallout. In this fractured world, tectonic forces had set the stage for life's final curtain call for dinosaurs and its opening act for new rulers. The breakup of Pangaea reminds us that Earth's surface is an ever-changing tapestry. As continents drift, we see how geography shapes evolution and extinction. The final fracture of Pangaea was more than a backdrop to the end of dinosaurs. It was an active participant in their decline and the crucible for the emergence of modern ecosystems. Part 29. Rapid Erosion. Mountains carved by the collision of India into Eurasia and the uplift of the Severe and Laramide ranges in western North America began to shed their rocks in torrents of wind and water, initiating rapid erosion that scoured ancient landscapes just as dinosaurs struggled to survive their final crises. Torrential rains from monsoonal shifts washed sediment from uplifted slopes into rivers, where powerful currents carved deep canyons and transported vast loads of gravel and sand. Fossil-rich floodplain deposits of the Hell Creek Formation show episodes where mighty rivers cut into floodplain soils, creating cross-bedded sandstone units filled with dinosaur tracks and bones reworked by violent floods. Remnants of these ancient river channels record floods so severe that entire herds of hadrosaurs and ceratopsians were swept away. Their bones jumbled together in chaotic bone beds that speak of death by drowning and burial in a single geological moment. As forests collapsed under acid rains, their root networks decayed, leaving soils unstable and vulnerable to landslides. Hillsides, once held firm by root mats, turned into mudflows that engulfed nesting grounds of nesting dinosaurs. Fossils of delicate eggshell fragments found in thick clay lenses of debris. Flow deposits reveal that dinosaur nesting behaviors, once reliable for millions of years, were undone by rapid erosion triggered by environmental upheavals. In coastal cliffs of Europe, chalk exposures record slumping due to wave undercutting, combined with rain-soaked soils, exposing dinosaur tracks in collapsing walls and preserving them in coastal talus alongside seafloor fossils buried by submarine landslides. Global warming pulses following methane release intensified the hydrological cycle, increasing precipitation extremes and driving flash floods across continents. Rainstorms peeled topsoil from plains, creating dust storms that added to the dust veil already choking sunlight. Paleosol profiles document erosion surfaces capped by thin silty veneers, marking intervals where soil formation paused and was erased by runoff. These episodic erosion surfaces appear in successive layers, indicating that the landscape was repeatedly stripped bare, then briefly revegetated by pioneering ferns and mosses before the next erosional onslaught dissolved those fragile anchors and reset the clock. In coastal deltas where rivers disgorged into shallow epicontinental seas, sedimentation rates spiked under this rapid erosion, building thick deltaic wedges that prograded seaward. These deltas entombed remains of marine and terrestrial creatures alike in mixed assemblages. Dinosaur bones mingled with fish scales and marine invertebrate shells, revealing how terrestrial erosion could transport land creatures far into the sea. Delta front deposits in the western interior seaway show fining upward sequences reflecting waning floods that nonetheless still carried coarse debris into marine settings, creating lethal brackish estuarine zones where fish and reptiles expired. Mountain headwaters scoured by glaciers and rainstorms delivered boulders and cobbles into canyon bottoms, where debris fans accumulated at valley mouths. In Patagonia, erosion of Andes uplift is recorded in alluvial fan deposits containing volcanic detritus that once blanketed dinosaur habitats. The mingling of volcanic ash and eroded sediment created cemented conglomerates trapping footprints of titanosaur sauropods and early mammals. These trace fossils immortalized the frantic final steps of creatures fleeing rising floodwaters, each print pressed into newly deposited sand now lithified into rock. Rapid erosion reshaped groundwater systems as well. As mountain belts rose and eroded, groundwater recharge zones shifted, altering spring and seep locations that many dinosaurs and early mammals depended on for water in arid seasons. Fossil tufa mounds, calcium carbonate deposits from ancient springs, appear in boundary strata atop sandstone beds, marking the spring's sudden failure when sediment clogged their conduits. The loss of dependable water sources added another layer of crisis, forcing terrestrial animals to travel farther and concentrate at shrinking oases where disease and predation intensified. As the deformed crust flexed under heavy sediment loads at continental margins, subsidence created new basins that rapidly filled with eroded detritus. In India, the lower Narmada Valley subsided under Deccan trap sediments, capturing thick sequences of sandstone and silt rich in dinosaur teeth and jaw fragments. These rapidly deposited sediments buried remains quickly, preserving a snapshot of the final Cretaceous vertebrate community in exquisite detail. Yet the very speed of burial ensured that ecological signatures were mixed. Fluvial reworking by floods blended remains of multiple species and ages, reflecting the tumultuous backdrop of rapid erosion. By the time the dust settled and waters calmed, landscapes lay stripped, rivers rerouted, and habitats fragmented by the relentless power of water and gravity. Rapid erosion at the end of the Cretaceous serves as a sobering reminder that even after the killers from sky and mantle have struck, the inexorable work of wind, rain, and ice can finish the job. In sculpted canyons carved from ancient floodplains, we read the final verses of the Dinosaur saga and the opening notes of a world where mammals, birds, and new ecosystems would rise upon the broken bones of the old. Part 30. Marine Regression. As the Earth reeled from impact winters, volcanic winters, and greenhouse pulses, the balance of land and sea shifted dramatically in a great marine regression. Seaborne waters that once flooded continental interiors withdrew to newly deepened basins, leaving behind vast coastal plains where saltwater marshes had thrived. In North America, the western interior seaway retreated, exposing a wide expanse of bare seabed that dinosaurs cautiously crossed in search of freshwater pools and vegetation. Fossilized stomatopod, burrows and scallop shells mingle in these regression deposits with dinosaur bones, illustrating how the sea's retreat created a liminal zone where marine and terrestrial life briefly overlapped before the final curtain fell. The regression began as global sea levels fell under combined effects of reduced tectonic subsidence, cooling from volcanic aerosols and impact dust, and glaciostatic changes from polar cooling pulses. Ancient carbonate platforms that once extended for hundreds of kilometers now lay exposed to air and sunlight, causing widespread karstification. In parts of today's Europe and North Africa, limestone outcrops bear deep sinkholes and cave systems that once formed in the latest Cretaceous as the water table dropped. These caves later filled with sediments that preserved batrachian amphibian fossils and the delicate bones of small mammals sheltering from surface hardships along the new coastline. Coastal ecosystems collapsed under these shifting shorelines. Estuarine nurseries where juvenile fish and juvenile marine reptiles thrived were choked by mudflat sediments as rivers extended their channels across the emergent shelf. Mosasaur remains in these deltaic deposits appear fragmented and abraded, indicating that as their feeding grounds vanished, these apex predators chased dwindling prey into turbid waters. In the newly formed lagoons, bottom environments became oxygen poor from decaying organic matter stranded by retreating tides, creating patchy refuges where only hardy invertebrates survived. On land, the exposed seafloor provided fresh grazing grounds for herbivorous dinosaurs at first. Soft marine muds rich in algae and collapsed coastal plants offering high nutrient forage. Yet this brief bonanza quickly turned into a trap. As dinosaurs traversed these flat expanses, they became mired in sticky sediments and caught in sudden flash floods from newly incised rivers. Bone beds in Montana and Alberta record mass mortalities, where hadrosaurs and ceratopsians perished together in mudstone layers, a haunting snapshot of herds caught by the unforgiving edge of retreating seas. The exposed shelves also altered weather patterns. The loss of shallow water heated faster than ocean basins, causing increased land heating and stronger monsoonal systems in some regions and aridification in others. In South America, the Amazon basin transformed from a vast inland sea to a seasonal floodplain with intense wet and dry seasons. Fossil wood from this period shows fire scars from lightning-induced grassland fires that spread unchecked across the newly dry terrain. These fires removed scrub growth and further expanded grasslands, offering new niches but also stripping shelter from dinosaurs and small mammals alike. Marine regression exposed continental slopes to vigorous erosion and landslides. As sediment loads shifted downslope, submarine canyons incised deeper and turbidites swept continental rise basins. In the western Pacific, the fossil record captures a thick sequence of deep marine muds, alternating with sand turbidites containing coral and foraminifera fragments, marking pulses of sediment avalanches that buried marine life at depth. These mass transport deposits record how the shrinking seas both fed and smothered deep ecosystems in equal measure. Despite the devastation, areas of refugia emerged along new coastal wetlands and river deltas where freshwater lenses persisted atop saline soils. These oases supported fish turtles and crocodilians, which adapted to the brackish conditions. Early mammalian ancestors colonized these margins, feeding on aquatic invertebrates and exploiting burrows abandoned by marine reptiles. Their success in these fringe environments foreshadowed the rise of mammals as the dominant terrestrial fauna once the last of the dinosaurs had faded from the newly emerged lands. In the wake of the marine regression, a new chapter of life began. Freshwater lakes formed in the former seaways, creating habitats for fishes, amphibians, and waterfowl ancestors. Soils developed on exposed seafloors, drawing pioneering plants that stabilized sediments and rebuilt ecosystems from scratch. Dinosaurs had crossed the threshold into this emergent world, only to meet extinction, but mammals and birds emerged to paint it with new evolutionary strokes. The story of marine regression reminds us that the shifting boundary between land and sea can both forge and erase worlds in the grand saga of life. Part 31. UV radiation spike. When the fragile armor of Earth's ozone layer thinned under the twin assaults of impact, induced nitrogen oxides and volcanic sulfuric aerosols, a silent killer, emerged in the form of an ultraviolet radiation spike that scorched the planet's surface. Ultraviolet B rays, normally absorbed by atmospheric ozone, battered exposed tissues of plants and animals alike. In equatorial regions near the Chicxulub impact site, plants bore sunburn patterns visible in fossilized leaf cuticles as deep etchings and pitting far beyond what acid rain alone could cause. These microscopic scars accumulated rapidly in boundary sediments, indicating that UV stress was intense and unrelenting for years before and after the asteroid strike. Marine phytoplankton suffered a parallel catastrophe as UVB penetrated into the photic zone, unfiltered. In modern experiments, increased UVB reduces photosynthetic rates by over 50% in key algal species. Fossilized diatom and coccolithophore shells in early Paleogene sediments show abrupt declines in abundance and diversity consistent with a major UV radiation event. The collapse of these primary producers triggered a food web collapse as zooplankton dwindled and fish larvae perished. Mass mortality layers of fish and reptile remains in boundary clay illustrate how animals reliant on plankton died off swiftly when their sunlit nurseries became deadly. Terrestrial herbivores like hadrosaurs faced both direct UV damage to unprotected skin and the indirect effect of diminished plant food quality. Plants under UV stress produce defensive compounds called flavonoids, which absorb ultraviolet and protect leaf tissues, but at the cost of reduced nutritional value. Analysis of fossilized tooth enamel from boundary hadrosaurs reveals shifts in carbon isotope ratios, suggesting greater consumption of flavonoid-rich foliage. This dietary stress, compounded by nutritional deficits, likely led to poor reproductive success and weakened immune systems, making dinosaurs more susceptible to pathogens. Ground-nesting dinosaurs encountered an even harsher environment. Eggs and hatchlings required incubation under sunlit skies but without ozone protection that sunlight turned lethal. Eggshell fragments from late Cretaceous nests show UV etching patterns and microcracks consistent with radiation damage to calcified tissues. Embryos trapped within these fossil eggs likely suffered developmental deformities and high mortality, as adult dinosaurs abandoned exposed nesting grounds in search of shaded refuges. They faced habitat loss and increased predation, a tragic trade-off between shelter and reproductive success. Insects that had co-evolved with flowering plants for over 100 million years found their ultraviolet-guided navigation disrupted. Many pollinators rely on UV patterns on flowers to locate nectar and pollen. When UV levels spiked, these signals became overexposed or distorted, confusing insects and reducing pollination rates. Pollen records from boundary sediments show reduced diversity and abrupt drops in angiosperm pollen, coinciding with insect decline. The breakdown of flowering plant reproduction further destabilized ecosystems on land and sea by collapsing mutualistic networks that had fueled the Cretaceous world's lush biodiversity. Freshwater ecosystems felt the UV spike as well. Amphibian eggs laid on water surfaces and juvenile fish, vulnerable to shallow sunlit waters, absorbed fatal doses of ultraviolet. Fossilized larval salamander and frog bones in boundary lake deposits often show bone lesions consistent with UV-induced DNA damage and bone development disorders. As adult amphibians succumbed to UV stress and disease, their absence left gaps in wetland food webs that had supported insects, small fish turtles and crocodilians. Wetlands dried out under intensified evaporation from stronger UV and greenhouse heating, further diminishing these critical nurseries. Surviving species sought shelter under dense canopies, caves, and underwater recesses. Burrowing mammals limited to subterranean dens avoided the worst of UV exposure and thrived in darkness. Aquatic species retreating to deep lakes or spring-fed pools avoided harmful radiation as water absorbs ultraviolet rapidly with depth. Fossils of early Paleocene mammals and fish appear concentrated in these refugia, indicating that survival favored those able to escape the sun's deadly rays rather than adapt to them. The ultraviolet radiation spike resonates in modern parallels of ozone depletion and increased UVB from anthropogenic chlorofluorocarbons. The end Cretaceous event reminds us that ozone is a delicate shield without which life on land and in oceanic shallows can collapse swiftly. As we piece together the fossil clues of UV-etched leaves and acid-etched bones, we learn that extinction can come not only from fire and flood, but from the sun itself, when its light is unleashed without atmospheric filters. Part 32. Habitat Fragmentation. As Earth convulsed under the combined assaults of asteroid impact, massive volcanism, sea level swings, and climate extremes, the continuous tapestry of Cretaceous ecosystems was torn into isolated patches, forsaking vast corridors of contiguous habitat for a fragmented mosaic of survivors' refuges. In North America, the Great Western Interior Seaways Regression left behind a labyrinth of rivers, wetlands, and upland plateaus, separated by inhospitable floodplains scarred by ash and dust. Dinosaurs that once roamed freely across hundreds of kilometers found their territories sliced by troughs of volcanic debris and new mountain barriers, forcing populations into genetically isolated pockets where inbreeding and local extinctions became grimly inevitable. The breakup of Pangaea intensified fragmentation further as drifting continents carried entire biotic provinces on divergent paths. In Gondwana's remnants, India's northward drift created an island that bore unique dinosaur faunas isolated from both African and Asian relatives. Fossil beds in the Lametta Formation preserved titanosaurs and abelisaurids whose lineages evolved in splendid isolation, adapting to insular environments before being overwhelmed by the extinction wave. These endemic populations, confined by tectonic barricades, could not escape to safer lands when global conditions deteriorated, sealing their fate in sedimentary tombs hundreds of meters thick. Marine regressions carved new coastlines that left once connected coral reef habitats stranded as reef islands separated by mudflats. Reef-dependent species such as reef sharks and mosasaurs retreated into shrinking patches of habitable water, only to find those refugia suffocated by hypoxia or acidification. Coral skeletons from isolated requinid mounds in the Gulf region record the last gasp of these ecosystems, their framework fragile under the weight of compounding stresses. As reefs fragmented, so too did the complex food webs they supported, unraveling the marine tapestry into disconnected strands. On land, rising sea levels in some regions offset regressions elsewhere, creating archipelagos that further carved dinosaur habitats into islands. In Europe and the Middle East, chalk sea inundations formed island chains where hadrosaurs and nodosaurs scratched out a precarious existence. Trackways on insular limestone show step lengths shrinking as individuals navigated crackling soils and seasonal water shortages. Islands that once offered refuge became ecological traps when powders of volcanic ash and dust smothered vegetation faster than isolation could foster new plant growth. Climate whiplash from impact winter to greenhouse surge drove north and south range shifts that became dead ends when plate movements obstructed migratory routes. Polar dinosaurs, accustomed to seasonal darkness, found themselves hemmed in by shifting coastlines and ice-rimmed seas. Fossil remains in Greenland's mid-Cretaceous formations reveal a final population of hadrosaurs that migrated along fjords before those corridors froze and glaciers advanced, burying their tracks beneath ice and debris deposits that would not yield their secrets until millions of years later. Fragmentation extended into subterranean realms as well. Burrowing mammals and small reptiles that sought shelter underground found their networks severed by volcanic flows and sediment slumps. Lava tube cave systems in the Deccan region were blocked by subsequent eruptions, cutting off entire populations from groundwater refugia they had relied on to survive acid rains and UV spikes. Cave deposits reveal layers of skeletal remains where generations of troglophiles perished in sealed chambers, their silent deaths chronicling the collapse of subterranean highways. Bird ancestors and pterosaurs, once masters of the skies, faced fragmented aerial pathways as atmospheric clarity fluctuated with dust veils and acid precipitation. Restricted flying corridors between emergent islands and mainland cliffs left pterosaur nests vulnerable to predation and environmental extremes. Fossilized pterosaur eggs atop chalk pillars in southern England speak of aerial creatures forced to lay in exposed high places, only to have hatchlings thrown to the winds by storms amplified in the post-impact climate. Even microbial communities experienced fragmentation at microscopic scales. Soil crusts of cyanobacteria and lichens that grew on cooled lava or ash fell into patchy mats, separated by sterile deserts of loose sand and salt flats. These primary producers could colonize only where moisture and light conditions briefly aligned, limiting organic contributions to soils in fractal patterns mirrored by the vertebrate fossils above. The fine scales of microbial habitat fragmentation echo the grand patterns observed in dinosaurs and mammals, reminding us that life's continuity relies on connected networks from the tiniest cells to the largest herds. The collapse of Cretaceous habitats into isolated fragments stands as a final testament to how the interplay of geological and climatic forces can sever the ties that bind ecosystems. In the broken remnant landscapes, life's threads snapped one by one until only scattered refugia remained. As we peer into this fractured world through the lens of fossils and sediments, we are reminded that connectivity is the lifeblood of biodiversity, and that when the grand corridors of Earth are divided, extinction can follow in a cascade spanning scales from global to microbial. Part 33. Competition Stress. As Earth's shattered environments pushed survivors into ever smaller refugia, competition stress soared to unprecedented levels, pitting species against one another in contests for diminishing resources. Herbivorous dinosaurs accustomed to lush floodplains found themselves pressed into sparse woodlands and scrublands where palatable foliage had thinned. Fossilized tooth-wear patterns in late Cretaceous hadrosaurs show not only abrasive scratches from fibrous plants, but also microstriations indicative of gnawing on bark and even bone fragments, a desperate adaptation driven by intense competition for limited food. As individuals jostled for the choicest morsels, social hierarchies became brutal arenas where only the strongest or most cunning could secure enough nourishment to survive the breeding season and ensure the next generation. Carnivorous theropods likewise faced fierce stress as prey populations collapsed under plant decay and habitat fragmentation. Pack hunters such as dromaeosaurs and tyrannosaurs, once thriving on abundant herbivore herds, turned to solitary scavenging under the pressure of competition. Bones from the Hell Creek Formation preserved tooth marks in parallel arrays, consistent with multiple individuals feeding sequentially on the same carcasses, indicating that scavenging replaced active predation as the primary food acquisition strategy. This shift intensified encounters with other scavengers, crocodilians, mammals, and even conspecific rivals, creating high-stakes standoffs captured in the fossil record as punctured skulls and healed bite scars where only the most dominant feeders prevailed. The influx of early mammals into shrinking niches added another layer of competition stress. Small nocturnal insectivores and omnivores shared burrows and foraging grounds with juvenile dinosaurs and reptilian survivors. Isotopic analysis of mammals' tooth enamel from boundary strata reveals overlapping dietary signatures between early placentals and juvenile ornithischians, suggesting direct competition for seeds, insects, and small vertebrates. In regions where competition peaked, mammal species show reduced body size and evidence of niche partitioning in limb-bone morphology, as some optimized for climbing into trees, others for burrowing underground, underscoring the intense selection pressures driving rapid morphological diversification under competitive duress. Avian dinosaurs and true birds found competition pressures, both from ground dwellers and airborne rivals. Early neo-avians searching for insect prey in the same brush piles as small mammals faced agile opponents with keen olfactory faculties and tooth-equipped jaws. Fossils of hollow bone perching birds in boundary layers reveal unexpected robustness and muscle, attachment scars hinting at powerful wing strokes used in aggressive aerial chases against other birds and insects. Competition for nesting sites in cliffs and tree hollows placed additional stress on cavity nesters, whose eggshells in some deposits show microcracks consistent with clutch abandonment, under attack by competing species or environmental threats. In marine realms, competition stress played out among shellfish and planktonic communities, battling for scarce nutrients in acidifying and hypoxic waters. Bivalves such as in oceramids, once dominant reef dwellers, dwindled under low oxygen, while opportunistic mussels expanded into vacated niches. Their fossils cluster in dense beds where they outcompeted slower-growing shelled organisms. Their thick shells and cemented basal attachments, an evolutionary response to high sedimentation and competition for hard substrates. At the microscopic level, diatom assemblages shifted towards smaller, faster reproducing species that monopolized nutrient pulses at the expense of larger forms, revealing competition stress driving rapid phytoplankton turnover. Competition stress also manifested in plant communities as rare survivors battled for sunlight in darkened skies and acidic soils. Pioneer ferns exploited the brief windows of light between dust storms, but were quickly joined by mosses and liverworts that clung to bare rock surfaces. These early colonizers competed fiercely for anchorage on volcanic ash deposits, their dense mats creating microhabitats that excluded slower-growing gymnosperms and angiosperm seedlings. Fossilized root traces in Petey's formation show overlapping rhizomes from multiple species interwoven, like arms locked in struggle, each vying for moisture and nutrients in hostile substrates. Amphibians and freshwater fishes felt competition stress as shrinking water bodies hosted crowded assemblages of survivors. Frog and salamander fossils in Devon Island lake beds occur in dense clusters with high incidences of spinal deformities and limb pathologies linked to crowding and poor water quality. Freshwater fishes developed morphological changes, elongated gill rakers and hypertrophied kidneys, in response to elevated competition for oxygen in stratified lakes. These adaptations illustrate how pressure from fellow survivors can drive rapid physiological change in dire environmental circumstances. Competition stress at the end of the Cretaceous was the crucible in which the next age of life was forged. As the great dinosaurs succumbed to the combined onslaught of cosmic and terrestrial catastrophes, the survivors, mammals, birds, and hardy reptiles, endured not only external threats, but fierce competition from kin and rivals alike. This relentless contest for life's dwindling prizes accelerated evolutionary change, laying the groundwork for the biodiversity of the Cenozoic world. In the silent witness of fossils, we learn that competition, when resources collapse, becomes both executioner and sculptor, carving new forms from the dying echoes of the past. Part 34. Toxic algal blooms. As nutrient runoff surged from eroded landscapes burned by impact fires and volcanic ash, coastal seas became fertile breeding grounds for toxic algal blooms that choked ancient marine ecosystems in a deadly flush of biological poison. Phosphorus and nitrogen delivered by weathered volcanic ash and acid rains fueled massive diatom and dinoflagellate proliferations in shallow Cretaceous seas. These explosive blooms turned waters to thick, soupy carpets that emitted biotoxins lethal to fish, reptiles, and even marine birds. Fossilized fish bones recovered from boundary muds exhibit lesions on gill plates and bone necrosis, indicative of toxin exposure, a haunting record of seas transformed into chemical traps. When the blooms senesced, their decaying masses sank to the seafloor, triggering oxygen depletion in bottom waters as bacterial decomposition consumed available oxygen. Expanded hypoxic and anoxic zones arose beneath surface mats, suffocating benthic communities that had survived earlier crises. Sediment layers show laminated black shales rich in organic carbon, where nothing lived to disturb settling particles. Among these dead zones, opportunistic sulfur bacteria flourished, producing hydrogen sulfide that further poisoned overlying waters. The spectrum of microbes dominating these layers shifted dramatically from diverse Paleozoic survivors to monocultures of bacteria well adapted to toxic low-oxygen conditions. Marine reptiles dependent on healthy food chains felt the brunt of these events. Mosasaurs and plesiosaurs hunting near coastlines encountered patchy prey fields as fish stocks collapsed under repeated bloom events. Fossils of long-necked plesiosaurs found in boundary clays sometimes preserve gut contents of sticky algal debris and resinous toxins, suggesting that these predators ingested blooms by mistake while pursuing small fish. Their resultant mass mortality layers capture individuals frozen in death throes, their skeletal articulation betrayed by carcasses caught in oxygen-deprived waters where scavengers could not reach them. Coastal gradients of bloom intensity shaped the survival prospects of different communities. Estuarine environments with freshwater input saw diluted blooms that waxed and waned seasonally, allowing some filter feeders and crustaceans to endure by burrowing or switching diets to detrital organic matter. Yet in open coastal shelves where nutrient pulses were strongest, blooms persisted for decades, entombing ammonites and bivalves in layers devoid of normal shell fragmentation. The differential bloom patterns underscore how subtle variations in water chemistry could decide life and death for entire faunas. Terrestrial ecosystems did not escape the influence of toxic algal blooms. Fish killed by blooms washed ashore, and decayed in shallow lagoons smelled of decay that attracted predatory dinosaurs and mammals. Paleontological sites show clusters of hadrosaur and dromaeosaur bones alongside fish remains, indicating mass scavenging events. Yet the meat of poisoned fish introduced toxins into terrestrial food webs. Carnivorous dinosaurs that feasted on carcasses may have suffered secondary poisoning, their bone growth rings during this interval, showing stunted annual layers consistent with chronic health stress. Planktonic photosynthesizers, the bloomers themselves, evolved survival strategies to endure episodes of high light and nutrient excess. Certain dinoflagellate lineages developed thick cell walls and cyst stages that sank to sediments during unfavorable conditions, only to germinate when waters warmed and nutrients returned. Fossil cysts in boundary sediments form dense mats of resting stages that could survive decades of darkness or cold before repopulating the seas. These cyst beds provide direct evidence of bloom recurrence in pulses that mirrored volcanic and climate cycles. Modern studies of harmful algal blooms reveal parallels in the Cretaceous event. Dinoflagellates produce toxins that disable sodium channels in nerve cells, causing paralysis in fish and mammals. In boundary layer sediments, researchers find elevated concentrations of organic compounds structurally similar to modern saxitoxin, hinting at ancient biochemical arsenals that shaped extinction patterns. The biochemical footprints of these toxins, preserved in kerogen and bitumen, allow us to reconstruct how blooms introduced chemical warfare into marine food webs at a time when physical disasters already ravaged life. In the aftermath of the toxic algal crisis, some species adapted by moving into deeper offshore environments shielded from bloom toxicity. Triassic survivors in deep basins found refuge where bloom mats could not reach, their descendants emerging as early Eocene fish and crustacean lineages. Terrestrial mammals that drank from deep wells or subterranean springs avoided the contaminated coastal waters, their early fossil occurrences clustered in upland regions away from bloom zones. These refugia stories illustrate how life can find shelter even in a world flooded by its own biological waste. The phenomenon of toxic algal blooms at the end of the Cretaceous reveals how nutrient and climate disruptions can trigger biological feedbacks that multiply extinction stress. In a planet already shaken by fire, ice, and cosmic blows, the dark green tide of algal toxins delivered a final blow to marine and coastal life. As we confront modern harmful blooms driven by agricultural runoff and warming seas, the ancient record offers a stark warning of how quickly the balance of nutrients and life can tip from abundance to poison, reshaping ecosystems with lethal rapidity. Part 35. Carbon Isotope Shift. In the final chapters of the Cretaceous, a profound shift in carbon isotopes rippled through Earth's carbon cycle, signaling massive perturbations in the atmosphere and oceans. The ratio of carbon-13 to carbon-12 recorded in organic matter and marine carbonates plummeted in a negative excursion that marked the boundary between Age of Dinosaurs and the new world of mammals. This shift reflected an injection of light carbon into the system, likely from massive volcanic degassing of carbon dioxide, methane release from destabilized hydrates, and the combustion of biomass in global wildfires. As this flood of light carbon drowned the stable isotopic signature left by millions of years of photosynthesis, scientists decipher these anomalies as fingerprints of multiple global crises converging in geologic instant. In marine sediments across many continents, the negative carbon-13 spike appears synchronously within clay layers enriched in iridium and shocked minerals from an extraterrestrial impact. Foraminifera shells that once recorded a steady carbon ratio suddenly exhibit values 3 to 4 per mil lower within a few centimeters of the boundary. This rapid fluctuation indicates the carbon spike occurred within decades or less in geological terms. Planktonic algae and coccolithophores, sensitive to changes in carbon dioxide and acidity, recorded their own stress as carbonate shell formation faltered in acidified surface waters. The result was a global signal preserved in skeletal remains that speak of a world awash in unstable carbon. Terrestrial plants likewise inscribed this carbon isotope shift into their tissues. Leaf wax biomarkers extracted from boundary soils show a pronounced drop in carbon-13 values that mirror marine trends. When plants fix carbon dioxide with lower isotope ratios, they create organic compounds that reflect atmospheric conditions. Analysis of molecular fossils reveals that from polar forests to equatorial floodplains, plants were forced to assimilate carbon dioxide enriched in carbon-12, whether from volcanic emissions or methane outgassing. This universal signature across habitats underscores the magnitude and rapidity of the carbon perturbation. The sources of light carbon remain debated, but multiple lines of evidence point to methane hydrate destabilization playing a key role. Methane in hydrates is extremely depleted in carbon-13 compared to atmospheric CO2. As ocean temperatures rose under greenhouse pulses, methane clathrates at continental margins and polar shelves released vast volumes of gas that oxidized into carbon dioxide in the atmosphere. This process would have amplified warming, fueling a feedback loop of further hydrate dissociation. The carbon isotope record's compatibility with models of hydrate release supports this scenario, marking methane as both culprit and catalyst in the terminal crisis. Volcanic degassing from the end of the Deccan flood basalts also contributed significant light carbon. As basaltic lavas erupted, they released volcano carbon dioxide that had been sequestered in Earth's mantle, characterized by low carbon-13 values. Over hundreds of thousands of years, the cumulative volcanic output shifted the atmospheric carbon balance. In boundary sediments, elevated mercury concentrations correlate with carbon isotope shifts, linking volcanic fallout to carbon cycle disruption. The combined impact of volcanism and hydrate release produced a cocktail of greenhouse gases that drove global temperatures beyond the thresholds tolerable to dinosaurian physiology. Wildfires ignited by impact heat and volcanic lightning further injected light carbon into the air. Biomass burning releases particulate charcoal and soot, but also carbon dioxide and methane as plant matter combusts. Pollen records from the boundary layer show spikes in charcoals and a temporary dominance of fire-tolerant species such as ferns and grasses. The carbon released by these fires added to the isotopic excursion, and as soot draped ancient skies, the combined effect of darkness and greenhouse gases created a deadly paradox of cold, sunless days, followed by searing thermal spikes. Geochemical models that integrate volcanic, hydrate, and fire sources reproduce the magnitude of the carbon shift observed in rocks. These models suggest atmospheric carbon dioxide may have risen from pre-impact concentrations of 500 parts per million to well over 1,000 parts per million within centuries. Such a rapid increase would have outpaced any biological feedback capable of reabsorbing carbon swiftly, leaving ecosystems to cope with acid rains, heat stress, and oxygen depletion without respite. The faint traces of carbon-13 within microscopic fossils thus reveal the tempo and scale of changes that overwhelmed the giants of the Mesozoic. Though dinosaurs vanished in the wake of this isotopic cataclysm, the carbon shift also seeded the recovery of new life forms. In the Paleogene, surviving plants and animals adapted to higher carbon dioxide and warmer climates, shaping forests and marine ecosystems distinct from their Cretaceous predecessors. The carbon isotope shift stands not only as a testament to destruction, but as marker of transformation. In those boundary strata, we read a story of carbon unleashed from rock to sky, of ice released into water, and of life's resilience in the face of global upheaval. Part 36. Ice Sheet Advance. As the tumult of the end, Cretaceous crises gave way to a cleaner atmosphere and stabilizing climates, Earth's poles teetered on the brink of glaciation. In the early Paleogene, cooling trends reversed the greenhouse swings that had followed impact winters and volcanic pulses. Oxygen isotope records from deep-sea foraminifera reveal a gradual increase in heavy oxygen ratios, signaling the growth of ice on continental shelves. In Antarctica, land that had once hosted temperate forests bowed under the weight of nascent ice sheets, transforming from groves of podocarp trees and polar dinosaurs to cold deserts blanketed by granular snow. This initial advance of ice began in high elevations, where atmospheric cooling allowed perennial snowfields to persist through summer. Mountain glaciers coalesced, feeding valley glaciers that scoured bedrock and carved U-shaped troughs in what would become the Transantarctic Mountains. Glacial striations etched into ancient limestone testify to these first icy forays into southern polar landscapes. Fossilized plant remains found in glacial till hint at dramatic ecological shifts. Pollen of plant groups once thriving gave way to spores of cold-tolerant mosses and algae, marking the transition from lush polar rainforest to glacial permafrost. Ocean currents responded in turn to the burgeoning ice. As Antarctic glaciers grounded on the continental shelf, they impeded thermohaline circulation by chilling surface waters and releasing fresh meltwater. This pulse of cold, low salinity discharge accentuated stratification in the Southern Ocean, expanding oxygen-rich cold currents northward while slowing equatorial upwelling. Marine sediments record this shift in microfaunal assemblages. Diatoms adapted to cold waters replaced their warm water counterparts, and cold water foraminifera thrived in nutrient-rich waters enriched by glacial runoff. The Southern Ocean's transformation under early ice sheets reshaped global climate by reinforcing polar cooling. Northern polar regions, though less extensively glaciated than their southern counterparts, also witnessed ice expansions. In Ellesmere Island and northern Greenland, early glaciofluvial deposits preserve braided river gravels overlain by till containing erratic boulders traced to distant uplands. These sediments testify to small ice caps and valley glaciers that spilled into corridors used by polar dinosaurs and early mammals. Fossil footprints of hadrosaurs near the paleopolar coast give way to tracks of burrowing mammals in later layers, illustrating how ice advance overturned ancient polar ecosystems and opened niches for cold, adapted fauna. Ice sheet advance generated vast proglacial lakes where meltwater accumulated at glacier margins. In Patagonia and the Arctic, sedimentary sequences reveal thick lacustrine deposits overlain by rhythmites of glacial varves, annual layers of fine silt and coarse sand that capture seasonal melting and freezing. Fossil fishes and amphibians in these lacustrine beds indicate that pockets of life persisted at glacier edges, exploiting meltwater refuges warmed by sunlight and geothermal heat. These fragile oases offered lifelines to cold-tolerant species emerging in a world increasingly shaped by ice. As ice sheets thickened and merged, glacial isostatic depression pushed continental margins lower, allowing seawater incursions into depressed basins. Glacial marine deposits in Antarctica preserve layers of dropstones, iceberg-rafted debris that plummeted into sub-ice shelf waters. In these dark under-ice environments, chemosynthetic communities thrived around geothermal vents, portending the evolution of deep Antarctic ecosystems uniquely adapted to life beneath thick ice cover. Such communities foreshadow modern discoveries of microbial and invertebrate life under the Ross and Weddell sea ice. Global sea levels fell in lockstep with ice expansion, exposing continental shelves and fossilizing coastal ecosystems. Dinosaur-rich formations along shallow Cretaceous seas vanished under terrestrial sediments as shorelines retreated. Coastal plant fossils give way to fluvial deposits of braided rivers and wind-blown loess soils atop exposed shelves. These newly emergent plains supported ground-dwelling mammals and early horses that foraged on tundra grasses, initiating the transformation of former seafloor into productive terrestrial biomes. In a few million years, the initial ice sheet advance set the stage for recurrent glacial-interglacial cycles that would dominate Earth's later Pleistocene narrative. Though only modest in comparison to later ice ages, these early ice sheets marked the planet's first step toward cryogenic extremes following a Mesozoic greenhouse. They illustrate how life's tapestry can be reshaped by slow climatic shifts, carving new landscapes of ice and snow that both annihilate ancient lineages and seed the evolutionary success of cold, adapted survivors. Part 37. Greenhouse Spike. In the wake of initial ice sheet expansion, Earth's climate swung once more toward intense warming in a dramatic greenhouse spike that reshaped ecosystems within mere millennia. Massive carbon reservoirs liberated by continuing Deccan volcanism and destabilized methane hydrates overwhelmed nascent ice sheets, flooding the atmosphere with greenhouse gases. In polar regions, ice retreated rapidly, and ancient permafrost thawed, releasing yet more methane into the air. Deep-sea records capture this warming in oxygen isotope excursions, as foraminifera shells shift to lighter signatures, reflecting ocean temperatures several degrees Celsius above baseline. This abrupt surge forged a hothouse world that challenged the cold, adapted life clinging to glacial margins. Tropical regions became sweltering under the intensified greenhouse. Rainforests that had recovered slowly after impact winter flourished in heat and humidity, but at the cost of oversaturated soils and rampant fungal growth. Leaf fossils from Paleocene deposits show enlarged stomatal gaps, consistent with high CO2 uptake, indicating plants tried to cool themselves by releasing more water vapor. Yet this transpiration drove stronger storm systems, unleashing torrential rains that triggered catastrophic flooding. Sediment layers in deltaic basins record multiple rapid flood events, each depositing thick sequences of sand and organic debris, teeming with drowned reptiles and mammals, victims of climate's convulsive overdrive. Marine realms experienced parallel extremes. Warm surface waters expanded into higher latitudes, dissolving thermoclines and reducing the ocean's capacity to absorb oxygen. Hypoxic dead zones burgeoned along continental shelves and in enclosed basins, starving benthic communities. Coral reefs, once resilient to earlier crises, bleached and dissolved under warm acidic waters, their skeletons replaced by microbial mats in the deepest layers. Fossil coral fragments in boundary deposits carry microboring patterns from fungi and algae, evidence that reefs collapsed not just once, but in successive episodes as greenhouse pulses waxed and waned. With both poleward corridors aglow in warmth, species once confined to equatorial bands spread into mid-latitude zones, creating novel ecological assemblages. Early mammals radiated into newly hospitable regions, evolving into diverse herbivorous and carnivorous forms in damp heat. Fossil teeth from Eurasian Paleocene plains reveal mammals with shearing molars specialized for tough rainforest vegetation. These mammals coexisted with archosaur survivors in a mosaic of forest, swamp, and savanna that defied Cretaceous norms, illustrating how life rapidly adapted to greenhouse extremes. Oxygen levels in the atmosphere fluctuated under shifting balances of photosynthesis and decay. As rainforests expanded, they drew down core fires and produced oxygen, offering temporary relief to beleaguered survivors. Yet rampant decay of organic matter in waterlogged soils and stagnant waters released carbon dioxide and methane back into the air, feeding the greenhouse feedback. Sedimentary charcoal from widespread fires ignited by lightning storms in these humid conditions suggests that periodic wildfires punctuated the hothouse, carving fire breaks in dense forests and resetting successional cycles in an environment teetering between lush growth and combustible dryness. Amphibians, once decimated by UV spikes and acid rains, re-emerged in swampy wetlands, their sensitive permeable skins adapted to high humidity. Fossil frog and salamander skeletons in Paleocene swamp deposits display bone microstructures indicative of rapid growth, facilitated by warm temperatures and abundant food. Yet these amphibians also faced new threats from lethal fungal pathogens, thriving in warm, wet conditions, a reminder that greenhouse spikes carry hidden biological dangers as well as climatic stress. Marine mammals and birds exploited open coastal waters warmed by greenhouse currents. Early whales appeared in newly formed seas, their ear bones preserving ear canal structures attuned to deeper, warmer waters. Fossil baleen whales in Tethyan strata indicate filter feeding strategies honed on plankton blooms fueled by high nutrient runoff under greenhouse storms. Seabirds developed salt glands to excrete excess salts from increased evaporation, enabling extended ocean voyages. These avian pioneers charted corridors across epicontinental seas that had retreated only centuries before under colder regimes. As greenhouse intensity peaked and then subsided in pulsating cycles, ecosystems settled into new equilibria shaped by warmth, humidity, and elevated carbon. Reef systems rebounded with new coral lineages tolerant of warmer, acidic waters, while forests gave way to mixed woodlands of angiosperms and early conifers. Mammals and birds held dominion on land and sea, their diversified forms reflecting the crucible of climatic extremes they had endured. The greenhouse spike thus stands as a testament to life's ability to adapt to rapid change, even as it underscores the peril of climatic upheaval on scales both ancient and modern. Part 38. Ocean acidification. Rivers swollen with volcanic ash, weathered from the Deccan traps and nutrient-rich sediment from rapid erosion, delivered a deluge of carbon dioxide into the seas, triggering a crisis of ocean acidification that rivaled modern concerns. As atmospheric CO2 climbed, more gas dissolved into surface waters, forming carbonic acid and lowering pH. The first to feel this acid assault were shelled plankton such as coccolithophores and foraminifera, whose calcium carbonate plates etched and thinned under corrosive waters. In boundary sediments, their microfossil remains appear fragmented and pitted, revealing the vulnerability of microscopic architects that anchor marine food webs. Coral reefs that had survived earlier cataclysms faltered under acidified conditions. Corals rely on aragonite saturation to build skeletons, and under low pH, their growth slowed dramatically. Reef outcrops in the Gulf region show abrupt cessation of coral framework and a surge in algal mats that colonize dead skeletons. These microbial mats thrived on dissolved nutrients, but lacked the structural complexity to support fish and invertebrates. Fossil fish teeth and reptile bones in overlying layers record mass mortality events, where predators hunted in barren seascapes, stripped of hiding places and prey. Beyond reefs, bivalves and echinoderms faced similar trials. Oysters and ammonites struggled to form their shells in acid waters, producing thinner and more fragile valves. Ammonite fossil assemblages in European chalk beds show narrowed growth bands and rarity of adult specimens, indicating recruitment failures. Sea urchins and starfish that consumed algae in shallow zones encountered skeletal dissolution that hampered their locomotion and feeding. Their decline echoes in fossilized sand dollars and echinoid tests, pocked with dissolution textures, marking acidified seas as a lethal chemical frontier. Marine reptiles endured indirect effects of ocean acidification as well, with base-level prey populations collapsing. Mosasaurs and plesiosaurs starved or faced toxic prey. Some reptiles may have ingested acidic seawater while pursuing fish, leading to gastrointestinal distress and weakened health. Fossil bones of mosasaurs show bone remodeling anomalies that parallel acid-mediated calcium loss, hinting that carbonate imbalance in their internal fluids undermined skeletal integrity. The last reptiles of the Mesozoic thus faced not only surface threats, but chemical warfare waged in their watery hunting grounds. Fish larvae proved especially vulnerable. Early development stages of teleosts and holocephalans require supersaturated aragonite conditions. Larval fossils in boundary layer deposits show deformities in otoliths. The ear stones used for balance, suggesting that acidified waters disrupted calcium carbonate deposition. Without proper balance and orientation, larvae sank into low oxygen layers where they perished. This recruitment bottleneck is echoed in modern acidification experiments, where high mortality in fish larvae foreshadows population collapse. If acid stress persists, subsurface waters became corrosive as acidification penetrated the thermocline. Deep-sea corals and sessile epibenthic communities, adapted to stable conditions, experienced shell dissolution and tissue stress. In deep Atlantic cores, subfossil coral fragments show thinning skeletal rings and encrusting bioeroders that tunneled into skeletons. These ancient deep-sea casualties highlight how acidification was not confined to sunlit shallows, but seeped into every ocean layer, undermining the very foundations of marine biodiversity. Amidst the crisis, some resilient organisms thrived. Pteropods, pelagic sea snails, adapted by thickening their mucus coatings to shield shells from acid attack. Certain foraminifera developed lower MG calcite shells, less soluble in acid waters. These adaptations appear in isotopic and elemental signatures preserved in microfossils, offering glimpses of evolutionary responses to chemical shock. Yet these hardy survivors could not replace the lost diversity, and their blooms created monocultures that supported only limited food chains. In isolated refugia such as alkaline seeps and hydrothermal vents, microbial and invertebrate communities persisted. These pockets of higher pH waters buffered against acidification, allowing calcifiers to maintain shell formation. Fossil seep carbonates, capping boundary sediments, capture these refugia in stone, preserving clam shells and tubeworm tubes that testify to life's tenacity. These deep-sea oases foreshadow modern hotspots of biodiversity that may one day shelter life from continuing acidification. The ocean acidification of the end Cretaceous stands as a stark preview of contemporary challenges. It underscores how rapid carbon inputs can overwhelm marine buffers and dismantle ecosystems in mere centuries. As we study the fossil traces of pitted shells and collapsed reefs, we are reminded that the chemistry of our oceans is as vital to life as its currents and temperatures. The lesson carried in those ancient seas warns us that chemical balance, once tipped, can accelerate extinction in both past and present oceans. Part 39. Lethal silica dust. When volcanic eruptions and impact wildfires throttled Earth's atmosphere with ash, the skies filled with silica-rich dust, so fine it remained suspended for months, becoming a lethal airborne scourge that invaded lungs and clogged respiratory tracts. These microscopic shards of volcanic glass, created by superheated rock vapor condensing mid-air, were razor-sharp at the cellular level. Dinosaurs, both small and gigantic, gasped in dusty loam, inhaled these particles deep into their bronchioles, triggering silicosis, like diseases that scarred lung tissue and impaired oxygen exchange. Fossilized rib fragments from late Cretaceous formations show porous bone lesions around air sacs, suggesting chronic respiratory distress as the fine dust abrading delicate lung membranes left irreversible damage. The cycle of ash fallout intensified with each pulse of volcanic and impact-triggered wildfires. Forest canopies rained charred leaves and embers that became incinerated into fresh ash upon contact with the hottest volcanic ejecta. This cycle created multiple layers of silica dust in boundary sediments, each one marking a pulse of environmental poisoning. Sediment cores reveal alternating bands of coarse tephra and ultrafine ash, the latter often enriched in cristobalite and tridymite, high-temperature silica phases known today to cause severe lung inflammation in miners and volcanic responders. As successive clouds of lethal dust drifted across continents, plants stomata ground to a halt, coated in glassy grit that blocked gas exchange and choked photosynthesis. Marine realms, usually buffered by vast water volumes, were not spared. Fine ash dispersed by wind settled on ocean surfaces, sinking slowly and abrading gill filaments of fish and filter feeders. Planktonic larvae, delicate in their development, ingested ash particles along with algae, leading to gut abrasion and blockages. Fossilized fish gill arches from boundary layers show pitting and scouring patterns consistent with prolonged exposure to abrasive particulates. Benthic organisms such as oysters and clams, anchored in shallow waters, found their feeding siphons blocked by settling ash, leading to mass die-offs documented in oyster bank collapse, horizons where thousands of shells lie unhinged on ancient mud flats. On land, herbivorous dinosaurs faced compounded silicosis as they grazed on ash-blanketed foliage. Tooth-wear patterns shift in boundary specimens. Microstriations indicate ingestion of silica dust mixed with plant matter, accelerating dental abrasion and reducing chewing efficiency. In massive sauropods, this meant less effective digestion of fibrous plants, triggering nutritional stress in animals already struggling under acid rains and UV assault. Meanwhile, smaller ornithischians such as ankylosaurs, scraping low vegetation, inhaled clouds of dust swirling near the ground, their robust nasal passages worn smooth in fossil skulls, evidence that even heavy-built reptiles could not escape the invisible razor storm. Mammalian survivors, though smaller, were not immune. Their endothermic metabolism required high oxygen exchange rates, but fine silica dust inflamed alveolar walls and caused pulmonary fibrosis. Early Paleocene mammal rib fossils display thickened bone collars around intercostal foramina, indicative of chronic respiratory infections. Yet some mammals thrived by exploiting underground burrows that filtered dust from the air. Their subterranean refugia, coupled with nocturnal lifestyles and fur-lined airways that trapped larger particles, allowed pockets of mammalian life to endure where dinosaurs faltered. Insects and small vertebrates suffered under impalpable ash too. Winged insects struggled as silica dust clogged tracheal tubes, leading to gas exchange failure. Fossilized insect exoskeletons in boundary shale show abrasions on wing veins and antennae, suggesting suffocation by glassy grit. Amphibians, whose permeable skin offered no barrier to dust, retreated to the mud along pond bottoms, but even these silted refuges filled with ash sediment, sealing eggs and larvae beneath impenetrable blankets of fine dust that smothered development. Ash clouds also carried chemical accompaniments. Heavy metals like mercury and arsenic vaporized from volcanic vents and impact melts. These metals adsorbed onto dust surfaces, hitching rides into lungs and water bodies. In boundary clays, trace metal concentrations spike alongside silica, combining physical and chemical toxicity in a double-edged threat. Fish and amphibians exhibit bone pathologies consistent with heavy metal poisoning, brittle bones and abnormal growth ring patterns, indicating that lethal silica dust bore a toxic payload as deadly as its abrasiveness. Recovery from the lethal dust storm required the resumption of rainfall to wash ash from foliage and oceans, and the rebuilding of the ozone layer to reduce UV stress that exacerbated respiratory damage. As plants recovered, they stabilized soils and trapped residual dust, gradually restoring air quality. Small mammals and birds emerged from burrows, their descendants inheriting adaptive traits, mucus-lined tracheae and rapid mucociliary clearance, that hinted at evolutionary memory of the Great Glass Storm. In coastal and deep-sea refugia, plankton and invertebrates recolonized the silted bottom sediments, their colonization layers preserving a transition from sterile ash beds to nascent benthic communities. The lethal silica dust episode of the end Cretaceous era stands as a testament to the power of geological and celestial forces to turn the atmosphere into a weapon of extinction. It reminds us that the smallest particles can wreak outsized havoc on respiratory systems, food webs, and ecological resilience. As modern civilizations grapple with volcanic ash hazards and industrial particulate pollution, the ancient record warns that airborne dust is a potent agent of ecological collapse when unleashed on a global scale. Part 40. Ecosystem Overturn. In the wake of intertwined catastrophes that felled dinosaurs, acidified oceans and poisonous ash, Earth's ecosystems underwent a radical overturn, unraveling ancient food webs and rebuilding new ecological architectures from the wreckage. What had once been lush floodplains teeming with sauropods and ornithischians became barren expanses choked by dust, acid rains and toxic algal mats. In these devastated landscapes, opportunistic pioneer species surged forward, only to be replaced in turn by successive waves of colonizers adapted to ever-shifting conditions. The static tapestry of Cretaceous life dissolved into a dynamic mosaic of rise and fall, extinction and innovation that reshaped the foundational relationships between plants, herbivores, carnivores, and the abiotic world. Terrestrial plant communities were the first to rebuild, as ferns and mosses capitalized on bare soils left by ash and erosion. These simple spore-bearing pioneers formed dense mats that stabilized sediments and created microhabitats favorable to small invertebrates and seed plants. Gymnosperms and early angiosperms followed in their wake, but the composition of forests changed fundamentally. Deciduous leaf types replaced evergreen conifers in many regions, reflecting adaptations to unstable climates with extremes of light and acid load. Pollen records from boundary sediments reveal rapid turnovers in dominant plant groups as ecosystems shifted from fern zones to mixed woodlands and ultimately to the deciduous forests that would characterize much of the Paleogene. Herbivorous dinosaurs gone, mammals seized the vacant niches with remarkable alacrity. Small multituberculates and early placentals diversified into specialized feeding guilds, from root diggers to frugivores, each exploiting resources overlooked or inaccessible to the giants. Dental morphology in early mammal fossils shows rapid innovation, with new molar patterns evolving in hundreds of thousands of years rather than millions. In floodplain environments where ferns dominated, mammals developed shearing teeth to process fibrous fronds. In riparian forests where angiosperm fruits emerged, they evolved crushing molars to crack seeds. This mammalian adaptive radiation laid the groundwork for later dominance of hoofed and carnivorous mammals as climates and forests matured. Aerial niches reopened as pterosaurs and most non-avian dinosaurs vanished. Birds diversified rapidly, evolving flight styles tuned to the open skies above emerging savannas and closed forests. Feathered limb fossils from early Paleocene deposits show variation in wing shape, corresponding to gliding, flapping, and soaring lifestyles. These avian pioneers exploited insect outbreaks and small vertebrate prey, often competing with arboreal mammals for canopy resources. Their success underscores how ecosystem overturn created not only open ground, but also complex vertical habitats that supported new arboreal communities. Freshwater systems that had been acidified and hypoxic regained balance as soils recovered and water flows stabilized. Fish lineages that weathered the extinction primitive teleosts and early catfishes expanded outward from refuge lakes and rivers. Sediment cores reveal increasing diversity in freshwater gastropods and bivalves, alongside improving carbonate saturation, indicative of recovering pH levels. Amphibians rebounded as wetlands reformed, returning their roles in nutrient cycling and insect control. The re-establishment of balanced freshwater ecosystems provided critical stepping stones for terrestrial survivors to access water and forage in redeveloping riparian corridors. Marine overturn mirrored land, with surviving plankton and invertebrates radiating into vacated niches. New calcifying organisms appeared, including early echinoids and gastropods, with adaptations to variable acidity. Reef ecosystems began to recover as coral relatives evolved more resilient skeletal structures. Fossil reefs in the Paleocene show thinner branches and denser frameworks compared with Cretaceous predecessors, an evolutionary response to lingering acid and temperature stress. Fish lineages rediversified, filling roles from small schooling forage fish to large apex predators distinct from mosasaurs and plesiosaurs. Predatory mammals emerged as apex hunters in the newly forged landscapes, their keen senses and endothermic metabolisms giving them advantages over reptiles. Early carnivora forms patrolled open plains and forest edges, their limb anatomy reflecting cursorial hunting strategies. Fossilized bone assemblages reveal bite marks from small carnivorous mammals on juvenile mammal bones, hinting at the rise of pack-like behaviors that would later characterize wolves and big cats. The rise of mammalian carnivores completed the overturn of trophic structures, replacing dinosaurian predation with a novel regime of mammal-based food webs. Insect and plant coevolution accelerated as flowering plants diversified under new climatic regimes. Pollinator groups such as early bees and butterflies co-evolved with specialized floral morphologies. Fossil flower structures in boundary-adjacent layers exhibit increased variability in petal shapes and nectar guides, signaling the establishment of complex plant-insect mutualisms that underpinned modern terrestrial ecosystems. These interactive networks spread across the globe, weaving the final threads of a radically transformed biosphere. The ecosystem overturn that followed the end Cretaceous extinction demonstrates life's resilience and adaptability. From dust-choked deserts to emerging forests and rejuvenated seas, Earth's biotic communities reassembled in novel configurations, each successive wave of colonizers building on the physiological legacies of survivors. In the fossil record, we trace this grand restart, marveling at how catastrophic collapse gave way to explosive renewal, and how, in the crucible of annihilation, the foundations of modern ecosystems were forged. Part 41. Nutrient starvation. Following the great upheavals of impact, volcanism and acidification, Earth's biogeochemical cycles collapsed, leading to widespread nutrient starvation that afflicted both land and sea. With soils eroded by acid rains and stripped by rapid erosion, essential minerals like phosphorus, potassium and micronutrients such as zinc were leached away before plants could re-establish deep root systems. Deep paleosol profiles reveal thick bleached horizons where clay minerals have lost their cation exchange capacity, leaving only nutrient-poor sandy substrates. In these barren soils, pioneering ferns and mosses tethered to strip mine scars of ash and dust survived briefly but provided little sustenance for herbivores, whose digestive systems geared to nutrient-rich vegetation faltered in meager conditions. Marine ecosystems mirrored terrestrial nutrient depletion as continental shelves, the primary sources of riverine nutrients, contracted under marine regressions. Rivers heavy with sediment from eroded volcanic landscapes carried phosphates and silicates into the oceans, but these pulses were sporadic and soon overwhelmed by acidified conditions that bound nutrients into unavailable chemical forms. Plankton blooms triggered by transient nutrient spikes quickly died off, and the subsequent decay consumed oxygen, creating dead zones that prevented deeper mixing of nutrient-rich waters. The result was a breakdown of the thermohaline pump, a vital conveyor of nutrients from abyssal depths to the photic zone, effectively starving phytoplankton and initiating a cascading collapse of marine food chains. In freshwater realms isolated by saltwater intrusions and regression lakes, nutrient starvation hit fish and amphibian populations hard. Lake sediments display laminated diatom mats, where diversity dwindled, leaving only species adapted to garbage can levels of silica and phosphate. Fish larvae, unable to find sufficient algae to feed on, show stunted bone development in fossilized otoliths. Amphibian larvae fared slightly better by grazing on microbial mats rich in nitrogen fixers, but their limited growth delayed metamorphosis and exposed juveniles to predators for extended periods, contributing to their local extirpation in many basins. Nutritive impoverishment also constrained terrestrial herbivores. Early mammals that managed to nibble on hardy roots and seeds faced crops with diminished protein and fat content. Stable isotope studies of mammal tooth enamel from boundary layers reveal elevated nitrogen-15 values, indicating they ingested poorer quality food, requiring greater trophic recycling. Carnivores preying on these malnourished herbivores suffered secondary starvation, their bones bearing marks of nutrient deficiencies such as porotic hyperostosis, a condition where bone marrow expansion leaves spongy lesions, indicative of chronic anemia. Plant-insect mutualisms frayed under nutrient stress as flowers lacking essential minerals produced fewer nectar and pollen rewards. Pollinating insects such as beetles and early bees recorded population crashes evident in pollen assemblages where insect damage on sporadic flowers declined sharply. The loss of pollinators further suppressed angiosperm recovery, creating a feedback loop where nutrient-poor soils and dwindling pollination hampered plant resurgence, extending the era of starvation across multiple growing seasons. Coastal wetlands and estuaries, once nutrient-rich nurseries, became sterile salt flats after sediment redistribution and salinization. In these transitional zones, oysters and crabs faced web starvation as detrital inputs collapsed and primary production from marsh grasses vanished. Molluscan shell chemistry records show lowered strontium and magnesium levels, signatures of metabolic stress caused by poor food quality. These estuaries, often the last refuges for both marine and terrestrial species, thus fell silent, their nursery functions erased by nutrient depletion. Some microbial communities adapted by fixing their own nitrogen or harnessing chemosynthesis in deep sea vents and cold seeps, where nutrients trickled from Earth's interior. These microbial oases, preserved as black smoker chimneys and seep carbonates, provided tiny pockets of organic production that sustained limited food webs even as nutrient starvation raged elsewhere. Tube worms and vent clams flourished, their symbiotic bacteria converting dissolved hydrogen sulfide into biomass, exemplifying how life can persist by sidestepping conventional nutrient pathways. Over hundreds of thousands of years, nutrient cycles slowly recovered as soils reformed, forests regrew, and weathering delivered mineral ions back into rivers. Phosphorus locked in volcanic glass dissolved with time, and ash layers mellowed into fertile loams. Freshwater and marine nutrient pumps restarted as bioturbation by burrowing organisms resumed, and thermohaline circulation gradually regained strength. Yet this recovery marked a new baseline, one defined by post-extinction ecologies in which life had to adapt to a leaner, harsher world. The era of nutrient starvation at the end of the Cretaceous teaches a sobering lesson about the fragility of nutrient cycles that underpin all ecosystems. When soils erode, waters acidify, and biological pumps break down, starvation can sweep across kingdoms, silent yet profound in its impact. As modern landscapes face nutrient depletion from erosion, pollution, and climate extremes, the ancient testimony of starvation reminds us that the threads of life's tapestry can fray swiftly when the elemental cycles that nourish us falter. Part 42. Catastrophic Tsunami. When the Chicxulub asteroid slammed into the Yucatan Peninsula, it displaced massive volumes of seawater, generating a series of catastrophic tsunamis that raced across ancient oceans with heights measured in hundreds of meters. These megawaves surged inland across low-lying coastal plains, obliterating habitats in a single unstoppable pulse. Sediment deposits along Gulf Coast margins record giant boulder fields and chaotic megabeds where the energy of these waves tossed blocks of carbonate reef and forest trees together in a jumbled mass. In one such deposit in Texas, the bones of marine reptiles and terrestrial dinosaurs lie entwined, testimony to a single cataclysmic inundation that united sea and shore in violent embrace. The tsunami sequence was not a solitary wave, but a series of pulses driven by the complex interplay of impact cavity collapse, seismic shaking, and gravitational oscillations of the ocean. Each pulse built upon the last, amplifying in height as it crossed shallow continental shelves. In the western interior seaway, wave heights estimated from run-up indicators approached 60 meters, overtopping barrier islands and backflooding into inland seaways. Marine sediments laid down during these events show alternating layers of coarse sand and fine mud, laden with marine microfossils, marking the pulse and retreat of waters that scoured the seafloor and then withdrew, only to rise again in relentless succession. In coastal forests, towering walls of water uprooted trees as if they were saplings, transporting timber inland where log jams dozens of meters deep formed choke points in new flood channels. Fossilized trunks preserved upright in fluvial sands reveal moments frozen in time when trees were driven into paleocanals by the first wave and buried by the second. Beneath those trunks lie leaf beds of fallen foliage, smothered by sand, preserving the last breaths of Cretaceous woodlands under a blanket of marine sediment. Dinosaurs dwelling near shorelines fared little better. Hadrosaurs and ceratopsians grazing in coastal meadows found no escape from the deluge. Trackways etched in shallow lagoon muds show herds charging toward higher ground only to be engulfed by the incoming wall of water. In one remarkable site in New Jersey, a sauropod footprint overlies a fish-scale layer deposited by an earlier tsunami pulse. The interleaving of marine and terrestrial traces speaks to the chaos of a world where land animals experience death by drowning alongside marine creatures driven inland. Tsunami deposits extend far beyond coastal plains. In interior basins connected by seaways, waves propagated into river systems, creating megafloods that carved new channels and deposited beds of marine sand, hundreds of kilometers from the nearest sea. In North Dakota, the Cannonball Sea left behind storm beds in the Williston Basin, where shark teeth and mosasaur vertebrae intermingle with terrestrial leaf mats. These inland tsunamis shattered the illusion of sanctuary from marine disasters, showing that even remote freshwater habitats were vulnerable to great oceanic pulses. The power of these waves also had profound ecological consequences. Nesting sites of dinosaurs on barrier islands were inundated and erased. Paleontologists have discovered clusters of eggshell fragments in tsunami megabeds, their embryos aborted by the sudden rush of salt water and sediment. Sea turtle ancestors nesting on sandy shores faced similar fates as tsunamis washed nests out to sea, drowning hatchlings before they could emerge. The loss of reproductive success in multiple clades amplified extinction pressures already mounting from other environmental catastrophes. Over the longer term, tsunami scouring reset ecological succession along coastlines. After the waves withdrew, sands blanketed former forests and marshes, creating new substrates upon which pioneering plants sprouted. Ferns and salt-tolerant grasses colonized these fresh sands, followed by shrubs and pioneer trees, adapted to high salinity and sand. Fossil pollen records show abrupt transitions from fern spores to grass and palm pollen in boundary layers, marking the rapid recolonization of landscapes reshaped by waves. The echoes of these catastrophic tsunamis endure in the geological record as chaotic megabeds that defy normal sedimentary layering. They remind us that when cosmic events strike, the interplay of water, land and life becomes a theater of unimaginable force. In those turbulent deposits we glimpse the final act of the dinosaurs and the dramatic opening of a world refashioned by water's immense power. Part 43. Bolide Swarm. In the moments surrounding the cataclysmic Chicxulub impact, Earth may have endured not a single cosmic strike, but a deadly cascade of bolides raining down in rapid succession. This bolide swarm would have delivered multiple smaller impacts scattered across the globe, each one amplifying the devastation of the primary collision. Shockwaves from the first impact fractured distant asteroidal fragments into a shower of secondary projectiles that resembled meteorite hailstones. Geological surveys reveal microcraters in regions as distant as Antarctica and India, clusters of pits mere meters across that speak to a sky filled with molten rock fragments plummeting through the atmosphere. These countless mini-impacts peppered landscapes with fiery debris, igniting brush fires, pulverizing exposed eggshells, and shredding the skin of any creature caught in the open. The bolide swarm's fury extended beyond direct strikes. Atmospheric entry of dozens or hundreds of fragments heated the air to thousands of degrees, creating firestorms of incandescent plasma that swept across plains and forests like a lethal wind. Heat pulses from these firestorms would have ignited vegetation in vast arcs, radiating from impact sites, hammering ecosystems already on their knees from dust veils and acid rains. In boundary layers rich in charcoal and paleosol ash, microscopic spherules exhibit outer rims melted by atmospheric re-entry, a testament to the uniform onslaught of incandescent fragments raining from a sky turned to a furnace. Each fragment's arrival sent localized shockwaves through the ground, triggering landslides and soil liquefaction in precariously balanced slopes. In the Hell Creek Formation, seismite horizons, laminated layers of disrupted sediment, occur at thicknesses inconsistent with a single impact event, instead matching models of repeated seismic jolts. These sub-meter disturbances captured animal burrows flattened and backfilled multiple times, preserving the desperate collapse of subterranean refuges under concatenated tremors. Small mammals that had saved themselves from surface chaos by burrowing found themselves crushed and buried in iterative ground tremors, evicted from their underground havens by unstoppable forces from above. Marine settings were not spared either. Fragments skimming across shallow seas generated mini-tsunamis and localized waves that pounded reefs and estuaries. In what is now New Jersey, beds of mixed marine and terrestrial fossils contain clams, fish and dinosaur remains, all entombed by sand layers deposited from rushing water triggered by these mini-tsunamis. The rapid alternation of wave pulses within the same stratigraphic sequence points to repeated ocean surges unleashed by consecutive bolide entries into coastal waters, a watery echo of the impact chaos on land. As the swarm rained down, airborne dust plumes from the primary impact mingled with fresh ejecta from each fleeting crash, prolonging the atmospheric blackout. Sunlight dimmed in waves, not just once but again and again, as each fragment lofted new dust into stratospheric currents. In boundary clay, microspherules from the bolide swarm carry chemical signatures distinct from Chicxulub ejecta, hinting that each fragment blasted unique mineralogical cocktails into the sky. These successive dust injections slowed photosynthesis in fits and starts, preventing any brief resurgence of plant life between impact pulses. The bolide swarm also injected a cocktail of volatile compounds into the air. Fragments vaporized upon impact released sulfur dioxide and nitrogen oxides that combined with water vapor to create acid rains more corrosive than those from volcanism alone. Widespread corrosion of fresh leaf surfaces appears in cuticle etchings far inland from known impact sites, evidence that chemical fallout from smaller impacts extended across continents. Lakes and rivers turned acidic repeatedly, leaving behind fish kills and amphibian larval losses captured in paleontological assemblages of stranded tadpoles and frog skeletons enmeshed in mudstone laminae. Remarkably, some niches briefly endured between swarm pulses. Burrowing creatures that survived initial shocks and heat pulses temporarily returned to the surface to forage in thin bands of daylight. Fossilized trackways of small mammals and lizards appear in thin ash layers, sandwiched between spheral beds, hinting at desperate forays into a world still hazardous, but momentarily quiet. These fleeting windows of calm, however, were shattered by the next rain of fragments, reminding us that in the face of a bolide swarm, survival was a cruel gamble of timing and luck. The bolide swarm scenario expands our view of extinction beyond a single impact. It evokes a sky strewn with burning stones, each one a potential executioner in a chorus of cosmic violence. In the fossil record, we observe the combined tomb of reptiles and early mammals, of plants and plankton, laid down by this relentless bombardment. The bolide swarm remains one of the most mysterious chapters in Earth's extinction narrative, a reminder that sometimes devastation comes not in a singular blow, but in a hail of cataclysmic fragments that leave no corner of the globe untouched. Part 44. Supercontinent Stress. The lingering legacy of Pangaea's fragmentation in the late Cretaceous set the stage for profound geological stresses that rippled through Earth's crust, exerting unseen pressures on the biosphere. As continental plates forged new boundaries, mantle convection currents responded by generating widespread intraplate stress fields that uplifted mountain ranges, triggered volcanic arcs, and reshaped basins. In western North America, the Sevier and Laramide orogenies warped sedimentary layers into towering ranges that rerouted drainage patterns and carved rain shadows. Dinosaurs inhabiting foothill environments faced fragmented habitats and microclimates, their migratory corridors bisected by rising peaks. Fossilized trackways that once traced seamless migrations across floodplains now end abruptly against thrust, fault scarps, a testament to how supercontinent stress could rewrite the map of life's pathways. Across Gondwana's southern reaches, stresses from India's northward journey caused the Himalaya precursor uplift long before the famed Asian collision. In Madagascar and Antarctica, rifts propagated inland, fracturing biotic refugia and isolating faunas in emergent microcontinents. Fossils from the Mahajanga Basin reveal endemic dinosaur species cut off by fault scarp barriers, adapting to unique climates forged by tectonic tilting. These populations, once free-ranging across vast southern plains, found their ranges shrinking under the shadow of rising crust, their genetic diversity confined by nascent mountain chains and deep fault valleys. As stress concentrated along plate margins, volcanic arcs flared to life, injecting ash and lava into the air and onto the land. The Proto-Andes in South America gained height as crustal shortening locked sediments into fold-thrust belts. Volcanic ash beds interlayered with dinosaur bone beds in Patagonia suggest that these pulses of arc volcanism coincided with local faunal turnover as herbivores retreated from ash-blanketed forests into distant valleys less afflicted by tephra. In these valleys, plant communities reinvented themselves on nutrient-rich volcanic soils, but dinosaurs adapted too slowly to exploit these refugia before the final extinction wave. In eastern Laurasia, subtler stresses shaped basins and subtropical archipelagos. The Izanagi Pacific Plate interactions squeezed the Japanese arc, uplifting islands and creating shallow marine straits that altered ocean currents. These shifts in water flow influenced regional climates, strengthening monsoonal rains in some areas and weakening them in others. Hadrosaurs and ceratopsians along Proto-Asian coasts encountered coastal swamp habitats renewed by tectonic subsidence. The rising and falling tides of emergent land also stranded herds on transient islands, as evidenced by fossilized beach trackways soon overlain by terrestrial soils. Supercontinent stress also manifested in inland basins that flexed under changing lithospheric loads. As mountain belts rose, adjacent basins dipped to accommodate displaced crust, creating deep rift valleys and playa lakes. In North Africa, the Tethys margins subsided into deltaic seas that preserved multi-layered bone beds of dinosaurs, crocodilians, and turtles. These basins, periodically flooded by marine incursions or lake expansions, alternated between aquatic and terrestrial phases, trapping organisms in cycles of drowning and burial. The rhythmic alternation of sand, silt, and shell beds in these basins captures the pulses of tectonic stress reverberating across continents. Deformation of continental interiors under stress also generated widespread seismicity. Earthquakes underpinned landslides that buried forest communities in mass-wasting deposits. In Europe, the Alpine Foreland Basin shuddered under pressures transmitted from the distant collision zones, triggering rock avalanches that entombed entire ecosystems in kilometers-wide debris flows. Fossil tree trunks and leaf mats found within these chaotic deposits paint a vivid picture of forests torn from slopes and carried en masse into flatlands where they were mired in rocky detritus. The stress of supercontinent rearrangement extended beyond geology into climate and sea level. Uplifted plateaus altered wind patterns, redirecting moisture away from coastal lowlands and creating new deserts in regions once verdant. In Central Asia, rising ranges blocked monsoons, turning floodplains into arid badlands, where only the hardiest dinosaurs, armored ankylosaurs and small theropods persisted. Oasis lakes in these now arid zones formed vital refuges where fossil deposits reveal herds gathering in precarious dependencies on scarce water sources. In the final million years before the extinction, supercontinent stress peaked as plates jostled for position and the lithosphere remolded itself under immense forces. These tectonic tensions interwove with the ultimate cataclysms of impact and volcanism, forging a world in which both living and non-living systems were pushed beyond the brink. The dinosaur saga thus unfolded, not only under cosmic and volcanic guns, but also within a globe cracked and reshaped by the slow yet inexorable forces of plate motion. a reminder that our planet's very bones can drive evolutionary dramas as powerfully as cometary collisions.